speaker, the second speaker here for this session. Yes.
Yes, it's the one that's supposed to be rolling.
Screen going? I don't think so.
Which microphone? Okay, the part.
Too afraid to touch him. I'm watching from
Then you can throw it.
I think we wait 2 more minutes if a technician can somehow lift the monitor. If not, we just start. Someone should come.
Unfortunately, I don't think there's anything they can do about it.
Okay, good morning. Welcome to the second day of VMCAI. We have our second keynote speaker, Hiroshi Uno. He got his PhD in Tokyo, University of Tokyo, 2009, continued in Tohoku University, sorry for mispronouncing it, and back to Tokyo, and now he's in University of Tsukuba in Japan. His research interest spans most of the VMCAI topics, I think, a lot of things, so automated software verification, synthesis, constraint satisfaction on optimization, automated theory improving, type systems, functional programming, applications of machine learning and verification and synthesis. And today is going to talk about automating relational verification of programs.
Okay, thank you for the kind introduction, and thank you for having me. Thank you for coming. Okay, it's my honor to present my ideas and thoughts on relational verification. Relational verification is verification of properties that relate multiple executions of one or multiple more programs. And Clarkson and Schneider formalized such properties as sets of program traces and coined the term hyperproperties. And K-safety is a notable subclass defined as a hyperproperty that can be refuted by observing K-finite traces. And relational verification is an important trend in formal method with applications including security. So I first show you some examples. Example hyperproperties first on multiple programs. A prominent example to safety is program equivalence. There are variants of program equivalence. Let me start with functional equivalence, that is input-output equivalence. The terminations insensitive version is defined like this. It says, if f of x returns some value y1 and g of x returns some value y2, they must coincide. And the termination sensitive version further requires that if f of x has a diverging execution, then g of x always diverge. Please note that this definition requires determinism. So it's too strict for non-deterministic programs. So a relaxed notion of equivalence can be defined as well, where the termination sensitive and non-deterministic equivalence can be defined like this, which compares the set of possible outputs for the given x. Okay? And the probabilistic version of equivalence can also be defined using the probability distribution of the outputs. And for reactive system, we often use trace equivalence defined using the set of finite and infinite execution traces of programs P and Q. And bisimilarity is also often used, which is defined like this. There is a strong bisimulation R such that P and Q is in the set. We also have, there is much work on observation equivalence, which says for any context C, C in P, if C in P evaluates to Y, if and only if C in Q also evaluates to Y. This notion captures non-trivial interactions between context C and higher order object-oriented and effective programs. And in security applications, attackers' capabilities are reflected in the definition of context. Okay, and let me next explain program refinement, which is the one-sided version of program equivalence. Let me start with functional refinement. Termination insensitive version of refinement is defined like this. If f of x returns y, then g of x returns y. And this is useful to transfer properties and proofs of programs to the other one. So if this holds, then we can transfer the partial correctness of z to that of f Okay? And the termination-sensitive version, which further requires that if f of x diverges, then g of x diverges, which preserve the total correctness properties. For trace refinement, it preserves trace properties of Q, which can be transferred to P. And similarity, which is defined like this. There is a strong simulation R such that P and Q in R. If P and Q are related by this similarity, then trace properties can also transfer to, from Q to P, but branching time properties cannot be transferred. By contrast, we can use bisimilarity to transfer branching time properties of Q to P. However, hyperproperties themselves cannot be transferred by using the bisimilarity. And as far as I know, there is no automated approach for synthesizing some program refinement that can transfer, that can be used to transfer hyperproperties, which is interesting. If you know some work, please let me know. Anyway, let me move on to the next slide. This slide claims that program refinement is a generalization of ordinary model checking. Program refinement verification generates ordinary model checking in the following sense, where a specification of P is given as a program Q instead of some logical formula phi. Q can encode the given phi if the language is expressive enough. Furthermore, Q can be a reference implementation or an abstract model represented as a highly non-deterministic program. Okay. And this motivates me to investigate entailment checking problems in a very expressive logic of first-order fixed-point logic module theories we call mu-CLP, and which is discussed in these papers. I will come back to this point later, relational verification via entailment checking in mu-CLP. And let me next show you some example hyperproperties on single programs. A killer application of relational properties is information flow, confidentiality, and integrity. For deterministic programs, there is a definition called termination insensitive non-interference, which is to safety, defined like this. Now, program F takes high security inputs H, and the definition is like this. For any high security inputs H1 and H2, and low security input X, and low security outputs Y and Y2, if F of H1X returns some value Y1, and F of H2X returns some value Y2, then they must coincide. This is a well-studied security policy formalizing the absence of information leakage from high security to low security. And the termination-sensitive version of non-interferences further requires that for any H1, H2X, if F of H1X diverges, then F of H2X always diverges. Okay? And we can also express timing attack resilience as a hyperproperty, but I will not go into details. For non-deterministic and concurrent programs, we can define other notion of other variant of non-interference, which is possibilistic non-interference, defined like this. Termination insensitive generalized non-interference is defined by this. It says that for any H1, H2, XY, if F of H1X returns some value Y, then F of H2X either diverges or returns the exact same value Y. Okay? The termination-sensitive version is simpler, which omit this condition. And we also have bi-simulation based on interference, but I will not go into details. Okay. And also, availability policies can be expressed as a hyperproperty, but I will skip this one due to time limitation. And algorithm analysis, robustness and sensitivity can also be expressed as hyperproperties, which I will not go into details. So yeah, let me skip it. And let me finally explain some specific use cases of hyperproperties. The first one is regression verification, which checks that the given program T is a refinement of the other program S for different versions T and S, where T is obtained from T is obtained from S by refactoring, bug fixes, or enhancements. And goal is to verify the absence of a software regression, that is a bug of T introduced by the modifications to S. Other useful cases are translation validation. It checks that T is a refinement of S for the source S and target T programs obtained by compilation or optimization to validate the translation. Okay. Other specific use cases include verification of an implementation of an abstract data type with algebraic specifications. For example, arithmetic operators such as mult and sum can be verified with respect to the algebraic specifications like equivalence, associativity, commutativity, distributivity, and so on. And please see the right table from my Cap 17 paper, which proves our tool can automatically prove such properties of mult, sum, and other functions. And another example is verification of list operations with algebraic specifications. Our tool can automatically verify property like this, which says that, appending list. So take XS and takes the first n elements of XS list, and drop XS and drops the first n elements of XS. And by appending them, we obtain the same list XS. Our tool can automatically prove it. All right, so let me set the goal on my talk, rest of the talk. Goal is to stipulate the, in my opinion, immature research field and hopefully find new research collaborators. I'm going to discuss the challenges in relational verification and introducing our automated relational verification method and highlighting the current limitations as well as future research directions. And here is the disclaimer. This talk will mainly deal with fully automated deductive relational verification and target functional properties. I will not address trace or contextual properties, and I will focus on infinite state systems that can exhibit effects such as non-termination and non-determinism, and will not cover other effects or finite state systems. Okay. And this is the outline of the rest of the talk, and let me next explain challenges in relational verification. Although each program execution is independent in relational verification, proving relational properties is challenging without reasoning about the correlation of intermediate execution traces. So analyzing each execution separately doesn't work well, as it necessitates an exact summarization of the input and output relation for each execution. Thus, an automated verifier is required to simultaneously synthesize the correlation of intermediate states, we call relational invariant, and a scheduler, or people call alignment, that preserves it. Okay? And let me briefly compare relational verification with concurrent programs verification. In concurrent programs verification, executions of programs that run concurrently can be highly dependent, as states can be synchronized with locks or semaphores, and data race can occur due to shared memory. So in concurrent verification, concurrent program is checked to satisfy the specification for all possible interleaving execution under a demonic scheduler. By contrast, in relational verification, multiple executions are independent, except for the inputs correlation. And it is sufficient to prove that the specification holds in a certain interleaving execution chosen by an angelic scheduler. However, to reason about the correlation between states at the time of output, it is still necessary to effectively synchronize other intermediate points as well. So therefore, the complexity of the verification is more significantly influenced by differences between programs. Okay, and let me use a program equivalence example to illustrate this point. These are two versions of multiplication functions. Okay, the first one, takes integer x and y and returns the multiplication of x and y. The second one is an optimized version of the first one, but the two are functionally equivalent. Here is an example execution of the first program, starting from 3 and 4, 3 for x, 4 for y, and returns 12. By contrast, this is an example execution of MAT2, and with the same input, the same output, but the length of the execution steps are different. So let's align the executions to preserve this property that we want to prove as much as possible. The initial states must be aligned. And next step, we can execute them in lockstep and obtain these states, which satisfy the property. The next step, though the structure of program at the program location B and E are different, but anyway, we can execute them in lockstep to obtain, to preserve the property, and we can again execute them in lockstep. Then the equivalence is broken. Okay. We can, however, recover the relation by using a stutter execution, by just scheduling the first copy, MAT1, to recover the property. And in general, we have to perform stuttery execution when this condition holds. Otherwise, we can execute them in lockstep. By using this alignment, we can, in fact, obtain a relational invariant preserved by the scheduler, which is sufficient to prove the property we want. However, how to infer such predicates, which is a challenge. In this example, we can obtain a predicate like this from the, extract it from the second program. But in general, we need to synthesize some useful predicates. So fully syntactic approach might not work here. Okay. Other example. Let me show you another example, termination insensitive no-interference. Let us consider this program, double square, which is obtained from this CAP paper, which computes 2 times x squared in 2 different ways depending on the high security input h. And so a question here is, can an attacker infer the value of h by observing the low security input x and the return value of y? Actually, this program satisfies termination insensitive no-interference, and attacker cannot infer the value of high security input. The property is defined like this, and let let us try to prove this one. However, first let us try the partial lockstep scheduler. Starting from the, so these are example execution traces. And please note that the low security input values x and y are equivalent. However, we assign different Boolean value to a high security input. Here, so preconditions, this one, x1 equals to x2. And by executing them in lockstep, we obtain these states which satisfy the property we want to prove. And again, a lockstep execution preserve the property, again preserve the property, but please note that here, copy 2 has exited the loop. And partial lockstep scheduler waits for copy 1 to exit the loop to synchronize. But this property no longer holds, violated. And so we cannot prove that this holds at the end. So a question, natural question here is, is there any simple but safe and inductive relation invariant preserved by the partial lockstep scheduler? Actually, the answer is no. There is no safe inductive relation invariant for the scheduler expressed in LIA, which is proved in this paper for this particular example. So in general, we need to come up with a clever scheduler. Okay. Let me next explain a code termination example, which is a hyperliveness property. Given these two programs, we want to verify that program 1 and program 2 agree on termination under the precondition, this precondition. Okay. So actually, yeah, these programs co-terminating. Co-termination can be formalized like this, and so this symmetric co-termination problem can be divided into two asymmetric co-termination problems. So let us prove an asymmetric version of co-termination. Let us try to prove it. So these are sample example execution of the two programs, starting from the same state. The first one, so in lockstep execution, like this, please note that the second program terminated before program 1. And we don't know how can we prove that this residual execution of program 1 always terminates. We need to solve this problem. And I will later explain how our method can deal with this example. Okay? And the last example is generalized non-interference, which is for exist hyperproperties. So this program non-deterministically returns a value x, which is greater than or equals to L, low security input L, but in two different ways depending on the high security input H. So they behave similarly, but the programs are different depending on the high security input. A question here is whether an attacker infer the value of H by observing the low security input L and the return value X. Actually, this program satisfies termination insensitive version of generalized non-interference, and attacker cannot infer information for high security inputs. Generalized non-interference is defined like this. Actually, this program also satisfies termination sensitive version of generalized non-interference. Please note that here, x1 in the definition is chosen demonically, while the value x2 is chosen angelically. So we need to somehow solve such games between universal and existential quantifiers. We also need to handle this problem. I will explain later how our method deal with this example. And there are other challenging examples in the literature which I will not go into details, but this program has loop tidying, this has loop splitting, and this one. Please note that the inner loop of the first program is summarized by this single statement, which is a bit difficult to handle automatically. And as far as I know, there is no single tool that can solve all of them. Anyway, okay, let me next talk about how to automate relational verification. Okay. There are two approaches, self-composition and end-term checking. So I will explain my previous work, published in POPL'21 and 70. And maybe due to the time limitation, I will skip most of the second part. But anyway, let me start with self-composition approach. Self-composition refers to a range of techniques aimed at synthesizing alignments represented symbolically as programs, automata, logical constraints, and games. There are many, many works. I listed some. And in my opinion, there are two approaches. One is syntactic one. Syntactic self-composition tries to use syntactic program structures and types to find interleaving alignment as a pre-processing for precise verification. And by contrast, semantic approach to self-composition tries to simultaneously synthesizing schedulers and inductive relational invariants within a verifier. So for alignment synthesis, we can use information obtained during analysis of programs to find a precise value-dependent alignment. And yeah, I will explain our approach to semantic self-composition. We soundly and completely encode the simultaneous synthesis problem relational invariants and fair and semantic schedulers needed for relational verification and represent it as a constraint-solving problem of the class we call PFWCSP that extends CHC's constraint home clauses with these new features. And here, head disjunction is used to express scheduler fairness constraints, and well-foundedness constraints are used for synthesizing code termination witnesses, and functionality constraints are used for synthesizing winning strategies for generalized non-interference. Actually, we generalize semantic self-composition for case safety presented in this previous work by others to GNI and co-termination. And for solving the extended class of constraints, we provided constraints over PCSAT based on the templates-based CGIS and answered core-based template refinement. So let me go back to the previous example of proving termination insisted with non-interference. Here, let me explain semantic self-composition for the TINI example. Our goal is to find a semantic scheduler as well as a safe invariant of the parallel execution of two copies of the program under the scheduler. And so by semantic, I mean schedulers can choose which programs to execute depending on the states. And our tool, in fact, synthesizes this scheduler, which states if this condition holds, then both copies move. And if this holds, only the first copy moves. So these are the example execution traces. Let us try to synchronize, align them with the scheduler, starting from the initial states. Because the first condition holds, we schedule both copies, and we align these two. And please note that here, this relation holds. Y1 is 2 times Y2. But next, we can again schedule both copies and obtain this property. But now, the first condition doesn't hold, and the second condition holds. So we only schedule the first copy to obtain this alignment. Then we recover the first property we had. And we can repeat this one. Next, we recover this one, and this one, and this one, and we can repeat this. And finally, we can show that this holds, and at the end of the program, we recovered this property that we want to prove. So this, for this scheduler, our tool synthesized. Our tool also can simultaneously synthesize this invariant, relational invariant, which is expressible in linear integer arithmetic. This is automated. Okay. And let me briefly show you how the synthesis problem is reduced to constraint solving. But I will not go into details, so you don't need to understand all of them. Here, predicate variable I represent a relational invariant, unknown relational invariant preserved by a semantic scheduler. And this part requires that the relational invariant is inductive and implies the property we want to prove. And this one, SCH predicate variables that represent the semantic scheduler. And if SCH1 holds, then first copy is scheduled. And these constraints represent the fairness condition of the scheduler, which says that at least one unfinished program must be scheduled if there is any unfinished one, which is necessary for soundness of our approach. Okay. Right. So we encoded this fairness condition using an extension of CSCs. Okay, let me next show you how to handle asymmetric co-termination using our semantic self-composition approach. Our goal is to find a fair semantic scheduler and relational invariant, and furthermore, we need to synthesize simultaneously well-founded relation to witness co-termination. For the example execution, so for these programs, our synthesizer automatically finds this scheduler, which is actually a trivial one. It says that if both programs are still running, then schedule both of them. And the second condition says if the first program is still running, but the second terminated, then only program one moves. So starting from the initial state, we can execute them in lockstep. And here, program 2 terminated. Difference from the previous scheduler is here. We can find well-founded relation that says that if program 1 is still running and program 2 is terminated, then program 1 repeatedly decreases x1. But x1 is lower bounded by 0. We can what to automatically synthesize this well-founded relation, but we need a relational invariant to support this claim, which is represented by this one. This says that if program 1 is still running and program 2 terminated, then the value of y1 must be greater than or equals to 1, which is actually a relational invariant preserved by this scheduler. We can use this invariant to show that when program 2 terminated, then program 1 eventually terminates, because program 1 always decrement x, the value of x. Okay, so let me next move on to the, this is how we reduce our synthesis problem to constraint solving. And again, I will not go into details, but briefly explain overview of the technique. Well, so I represent a relational invariant and preserved by the scheduler, and we have this one, R down arrow, which represents a well-founded, unknown well-founded relation, witnessing the termination of program 1 relative to the termination of program 2. Okay? And these constraints require that the relation invariance is inductive, and along with the well-founded relation implies co-termination. And this part says that the scheduler is fair. In this case, fairness is defined like this. All unfinished programs must be eventually scheduled, which is a stronger notion of fairness compared to the previous one, and which is necessary for the soundness of our approach for co-termination. Okay, and okay, I will skip these details. And we also have, I'll skip details. And the last example, semantic self-composition for termination insensitive, sensitive GNI. We need to find witnesses, fair semantic scheduler, relational invariant, well-founded relation, and also we need to synthesize strategies for the non-deterministic choices of the NGX side. And so to this end, we augmented the encodings for TI and I and coterm with predicate variables that represent the strategies, scoring functions, total functions from states to choices of the NGX side. We also added prophecy variables that represent the final outputs of the demonic choice, demonic side, which was necessary for the completeness of our encoding. Okay, and sorry, I will not go into details. Please refer to the paper if you're interested. And we have implemented the approach and evaluated on simple but small but very complex examples. And our solver, though it is not very efficient, but it anyway solved 15 out of 20 fully automatically, and only 5 required small hints. Anyway, so the tool PCSAT is a part of our core verification and synthesis tool chain, which I have been developing. And yeah, there are other tools, backend solvers and front ends, OCaml front ends, and so on. So please, if you're interested, please try to use it. And if you have any questions, please let me know. And let me discuss the approach. Semantic self-composition has a high theoretical potential and a promising experimental result, but actually some promising results have been obtained. However, I think current limitations are as follows. Relational verifiers based on semantic self-composition exhibit increased search cost and reduced efficiency as the capability of representable schedulers grows. So future direction is to leverage various existing syntactic and semantic abstraction, search pruning, and symmetry breaking techniques to accelerate the search. Okay. Okay. I think I have maybe. How much time do I have? 20 minutes. 10 minutes. Thank you. Okay, let me then briefly explain the entailment checking in MuseLP, first order fixed point logic. So please recall the slide I presented before, which claims that relational verification boils down to entailment checking in MuseLP, a fixed point logic. Let me use an example. Function program and its relation specification. These are two versions that implement multiplication, which the second one is an optimized version by tail call optimization. Okay, and this is the relational specification of mult and multac. Our tool can automatically prove this one, and these function programs, verification problems, relation verification problems can be reduced to CHE solving problem. But existing CHE solvers cannot solve this one because separate analysis of predicates P and Q involves nonlinear arithmetic. Okay, this part, multac corresponds to Q, and assertion corresponds to this one. And so CHE solving can be reduced to entailment checking in a fixed point logic. So this slide exemplifies the reduction. The right-hand side CHC is satisfiable if and only if the following entailment holds in a fixed point logic. So P and Q are defined using the least fixed point operators, which represent the least fixed interpretation of the definite clauses. And if these two imply the goal property, then CHC has a solution, and vice versa. Okay. So, this slide formally defines our fixed point logic, but this is not relevant to the rest of talk. I will skip this. And so the entailment checking, and we have presented an inductive proof system for entailment checking in the fixed point logic. This one, we prove this one, entailment, by induction on derivation of the definition of P. Here, this is the principle of induction of derivations. When we prove that property psi holds for derivation D, we can assume psi holds for all strict subderivations. We will use this principle to prove this relation property. Okay, so this one, home clauses are reduced to inductive theorem proving. And here, this is our judgment. This part represents a set of induction hypotheses and lemmas, and these are premises. Okay, we first apply induction rule to the predicate P and obtain an induction hypothesis of this form. And this part represents a guard to avoid unsound application. Okay. And then we next apply unfold rule to the predicate P and perform case analysis on the last rule used to derive P. And we obtain two subgoals. I think that, yeah, and in the subgoals, to prove the subgoals, we can use the induction hypothesis. They can, so let me try to prove this one, the first one, which is actually easy. We can unfold Q to obtain these two subgoals, but they can be automatically discharged by using an SMT solver. Only interesting case is the combination of these two rules. Here, let me skip the not interesting cases. Here, we have this subgoal when we apply these two rules to P and Q. Here we have recursive occurrence of P and Q, but with different arguments. We can here apply our induction hypothesis to discharge these two, to replace these two with this pure formula without predicate. So induction hypothesis represent relational invariant here, and we can apply relational invariant to close the proof. Finally, we can use an SMT solver to discharge the proof obligation, and we are done like this. And our approach is sound. If the goal is proved, the original constraints have a solution, and it's relatively complete. If the CHE have a solution expressive in the background theory, then the goal is always provable, and so on. And we have automated induction. We use the following rule application strategy. We repeatedly apply induction hypothesis until no new premises are added, and then apply valid, which is an SMT solver, whenever a new premise is added to close the leaves. And we select, otherwise we select some predicate in some heuristic manner and apply induction rule, and unfold. This simple strategy is adapted in our tool. And for closing a proof branch, we applied valid rule, where we use SMT solvers, which is powerful, which provides efficient and powerful reasoning about reasoning power for data structures, integer reals, and so on. And we can also use CHE solvers to discharge some proof obligation, which can handle inductive predicates as well. We have implemented in our tool music, which is available from the web interface. So our tool currently support entailments expressed in the fragment corresponding to CSCs. And entailment of this form can be handled. Furthermore, we can handle entailment of this form, where the head is replaced by the least fixed point, inductive predicate, which is clearly a strict generalization of CHC. And this is actually useful for program refinement verification and providing lemmas to prove entailments in the CHC fragment as well. And actually, we have done so. For commutativity proof of MUD, I have used lemma. Oh, can you see that? Anyway, yeah. So I used lemmas of this form. We have proved them and used these lemmas to prove relational verification problems. Okay. And yeah, our solver can prove and exploit lemmas which are user-supplied, heuristically conjectured from the given constraints, or automatically generated by an abstract interpreter. And our tool can generate a counterexample, if any. Okay. So I think I'm running out of time and out of time, so I'm going to wrap up. Okay, experiments and discussion. So the integration of SMT solving, CSC solving, and inductive theorem proving resulted in an automated relation verifier that can verify relation properties across programs in various paradigms, advanced language features, and side effects. And but however, the current limitations are these two. It has limited support for automatic lemma discovery and goal generalization, which are necessary for some examples. And it doesn't support the full fragment of fixed point logic. So future directions is to generalize recently observed connection to co-inductive improving to invariant and ranking function synthesis and software model checking to the full fragment of the fixed point logic. Okay? And these slides show the current limitations of both approaches. It often becomes impossible to establish program refinement and equivalence when there is movement of statements across loops or recursions. Examples include loop invariant code motion and loop interchange, loop fusion, which are problematic. So using commutativity or idempotency at the right times may help establish program refinement or equivalence, but more research is clearly needed. Okay? And so ongoing and future work as follows. We have developed a general theory. So we need to develop a general theory and algorithm for aligning reordered executions. And we need to improve the efficiency of semantic self-composition by incorporating abstraction, pruning, symmetry breaking. And interesting directions are to automate relational entanglement checking in the full class of the fixed point logic. And I'm also interested in temporal relation properties and probabilistic relation properties. Okay? So this is the conclusion. Okay, relational verification amounts to synthesis of relational invariants and schedulers, and emerging semantic self-composition techniques enable precise alignment, but requires further development to be refined into an efficient tool. An alternative approach I presented is based on entailment checking in a fixed point logic, first order fixed point logic. It shows some promise, though it requires more automation through the adoption of software model checking and other techniques to fully realize the potential of this approach. And in both automated approaches, aligning reordered executions remain a challenge. Okay. And yeah, the last slide, I'd like to acknowledge this talk is mostly based on these two papers, and I'd like to acknowledge my collaborators, Tachio, Eric, and my former students. Okay. And okay, that's all. Thank you very much for your attention.
Thank you very much for the talk. Interesting. Questions? Yes.
So your example talks did not contain procedures. Can you handle programs with procedures?
Oh, actually, the mod function can be considered as procedures, this one. So I have implemented a relational verifier for higher-order functional programs, or CAML, which contains recursive functions. Oh, sorry, this example.
And so then you infer summaries?
Oh, yeah, infer summaries. So this one, predicates P and Q represent the post condition of the function, which summarizes the input-output relationship.
Can you handle integer overflows?
Actually, so the second approach is based on SMT solvers for reasoning about data structure. So if the underlying SMT solver supports some overflow and floating point stuff, then our method can also deal with it.
I have a question. I have a question. So you mentioned simulation in the beginning. Is simulation expressible somehow as constrained on clauses?
Okay, so your question is how to encode simulations as constraint home clauses.
Right.
Actually, I think constraint home clauses is not expressive enough to encode simulation. So we have extended the class of CSCs to we called PFW CSP, which kind of support existential quantifiers or Skolem function synthesis, which are needed to deal with simulation.
More questions?
So you mentioned verification of high-order programs, and I was wondering, what about effectful programs, like especially when there is like dynamic allocation or this kind of problems?
Dynamic allocation. You mean stateful programs?
Yeah.
Oh, it's a hard question. So currently, our tool doesn't support mutable states. But yeah, so our tool is based on dependent refinement type system, and we are currently extending the dependent refinement type system to effectful programs. We have recently extended our refinement type system to delimited continuations and algebraic effects. So my collaborator will present that work at POPL, so please come. And but we have not yet worked on stateful programs. Maybe we'd like to support them by using ownership types or something like that. But yeah, it's a future work. Thank you.
Thanks.
I mean, I want to say first that I think you have your hands full, even without all the memory stuff. So there's plenty to occupy you. My question is that you talked about aligning reordered executions. I'm sorry I missed the early part of your talk. Is this what, in classical verification literature is referred to as automatically finding a simulation relation between two different transition systems? Or is it different somehow?
Actually, so I'm not familiar with that area. So maybe that classical result can be applied to this one. But yeah, but for synthesizing NGX scheduler, I'm not sure what are challenges there. But yeah, thank you for the comment. Clearly related.
Final question? Okay, if not, let's thank Hiroshi again.
Okay, thank you very much.
I have more questions later, offline. Okay. We have now two more talks, a regular talk and a shorter talk about a tool paper. And this next talk will be given by Philip Tasche from Twente University about deductive verification of parameterized embedded systems modeled in System C.
Yes, thank you very much for the nice introduction. And together with my colleagues Raoul Monti, Stephanie Drerup, and Pauline Blom, as well as my supervisors Paula Herber and Marika Hausmann, I've been working on a verification approach for embedded systems, which are systems that are embedded in a physical environment and interact with it through sensors and actors. And specifically, we've developed a deductive verification approach for the System C design language, of which I will give the key ideas and motivations in this presentation. So first of all, verification approaches for System C already exist, which are based on various varieties of model checking. Model checking, of course, has some advantages as a verification technique. It is very automatic, and there's, for plenty of applications, there's optimizations you can do. But fundamentally, it always struggles with large state spaces, be that through combinatorial state space explosion or through unbounded data ranges of, for instance, unknown program parameters. And so we wanted to use a different approach, and we decided on deductive verification. Instead of exploring the state space of a program, deductive verification uses a logical inference to deduce that a program complies with the specifications. And this has some advantages. It can be done at a local level in a modular fashion on the method level. And it easily supports unbounded values through symbolic execution. So the verification approach kind of looks like this. The user provides a System C design and some requirements that this should fulfill. And our approach then encodes both the design and the requirements in the prototypal verification language, or PVL for short, which is an input language of the Vercor deductive verifier, which we then use to verify the program. In this talk, I'll be going over these components of the approach. I'll first talk a bit about the fundamentals, the tools that our approach is based on, and then I'll go over the contributions of our paper, first the automatic encoding of System C and PVL, and then a bit about the verification techniques that we've developed. And at the end, I will also briefly go over the evaluation we've done. Starting with the fundamentals, System C is a C++ library that extends it with constructs for time and event reactivity and some hardware data types. It's often used in hardware-software co-design, and the idea is that a design is organized into modules, which could represent either hardware or software components, or something that has not yet been decided, whether it should be in hardware or software, which can then communicate with each other through defined channels, and define concurrent processes to encode the behavior of the system. These are then run by the System C simulation engine with its cooperative scheduler. And while they're concurrent, they are not actually in parallel. So in System C, there's only ever one process executing at a time, which the simulation engine then simulates parallelism by only advancing simulation time after all the processes have executed. These processes can interact with each other through events. So a process could wait for an event and another process notifies the event to wake the other process up. This can be immediate or time delayed, or processes can also just wait for a certain amount of time directly. This concludes my very brief introduction to System C. Going on to Vercor. Vercor is a deductive verifier developed at the University of Twente. It specializes in verifying concurrent programs and supports a variety of input languages, of which we care about the prototypal verification language PVL. You can see an example there in the bottom right. Its syntax is similar to Java, and it has some other inbuilt keywords for verification. The reasoning in Vercor is contract-based, so the user specifies for each method a method contract with pre- and post conditions using the keywords requires and ensures respectively. And then the prover will automatically try to establish that given the precondition and the method code, the post condition will hold after method execution. VMCAI supports a variety of models of concurrency, of which we use threads that are synchronized with locks. So now that the fundamentals are out of the way, onto the contributions of the paper. First of all, the transformation from System C to PVL. To encode a System C design in PVL, we need to take care of two components. The design itself, of course, but also the semantics of System C, which is very different from PVL. So encoding the design is relatively straightforward. Each process is mapped to a thread class in PVL. And if a module in the System C design contains multiple processes that share data between each other through the module, then this module is also transformed to a data class that the thread classes can share an instance of to share data that way. More interesting is the implementation of the System C semantics. System C implements its own scheduler, so we implement a scheduler thread that runs in parallel to all the process threads in our design, and which uses some global variables that encode the current state of all the processes and events in the design to encode the event and timing mechanism that System C provides. And finally, our encoding also contains a global lock that all processes have to, all threads have to hold to execute, so that just like in System C, we have only one process executing at a time. Now, to give an example of this, this is a very simple System C process, a sensor process that every 2 milliseconds polls a sensor, and if the data it reads is below a certain threshold, it reacts in an abstract way. In this case, it just sets a flag. So to transform this to PVL, first transform it to the run method of its thread class. And you can see here the method body is kind of framed by this lock and unlock statements, which means that the thread has to hold the global lock in order to be able to execute. Then most of the functional code can just be translated quite easily, but the wait statement, the timing component in line 3 of the original example is something that PVL doesn't support natively, and so we have to encode it some other way. In this case, this is a timed wait in System C, and we encode this through the event and timing mechanism. So we create another event and notify it with a delay of 2 milliseconds, and then immediately wait on this event to encode waiting for 2 milliseconds. So to start the process, at this point has to set the state of the event and itself. It sets the status of the event, which happens to have ID 1, to 2, which means it will be notified in 2 milliseconds. And then it sets its own state to 1, which means that it is waiting on ID 1. And this encodes the waiting for the event. And then the process just spins in a busy wait until the scheduler has made it runnable again because the event has occurred. Until then, it continues to unlock the global lock and lock it again so that other processes can execute in the meantime. And in this way, we can encode the semantics of the System C design in a PVL program, which we can then use as input for VMCAI. However, we still need to put in some work to be able to verify interesting properties about it, and so that's the second contribution of our paper. For the properties, we distinguish between two types of properties, which we call functional properties and global properties, depending on how difficult they are for us to deal with. Functional properties are those that are that are very easy to deal with. They're the typical deductive verification properties. A method contract that describes how the output of the method depends on the parameters would be an example of this, or an assertion about a local variable that can be verified just looking at the code of the method alone. Deductive verification is very good at this, and so we have no issues with this. Global properties, on the other hand, are those where this doesn't work, that depend on the global behavior of the system as a whole, not just one single method, that involve timing, for instance, that involve the interaction between different processes, the sequence of events that occur. These are not verifiable just on the local level where the prover is looking, and so they're quite hard to verify directly with deductive verification. However, many properties in embedded systems that we're interested in, especially timing properties, for instance, are of such a global nature, and so we need to figure something out in this regard. So what we need to do is to give the prover on the local level information about the global state so that we can reason about it. And the solution for this that we've come up with is to define a global invariant that we associate with a global lock, so that at every point at which a process releases the lock, and so there might be interleaving between processes, this global invariant needs to hold. And every time a process acquires the lock and is able to execute, the prover knows that now the global invariant holds, and it can deduce something about the state of the program. This is an example of such a global invariant, and you might be able to see here, highlighted in blue, there's a part of this that looks quite structured, which is directly related to the property that this allows us to prove. However, there's also a lot of random looking invariants in orange above it, which please don't try to understand these. These are very esoterical, and I just put them in to illustrate the point that this takes a very high user effort to come up with these invariants. In fact, while the verification time of a program with this invariant might be very low, only a few seconds, coming up with this invariant for us took about 8 hours, about a system that we knew very well already. So this is infeasible, prohibitively expensive, so we need a solution for this. The solution for high user effort, if possible, is automation. So the question is, can we automate this process? And the answer is yes, kind of. Because it turns out that many of these chaotic esoterical invariants here, their purpose is not to encode a property, but to restrict the state space that the prover considers during verification, so that it doesn't think it's in an impossible state, and so fire a spurious verification failure. So instead of encoding this with some clever manual invariants, we can just enumerate the state space that is possible, kind of leaning on ideas from model checking here, and encode it in this way. So this is what this looks then. These variable valuations there encode one state in a very abstract way. So that's the advantage of this. This is only supporting the verification. So it can be at a very, very abstract level, only talking about really the variables that are absolutely necessary and no data variables, parameters, and so on. And the actual verification about these variables will then happen at the local state using deductive verification, which is very good at this. And then we will just have a big disjunction of these states to encode the state space of the program. This can be very large, but it is automatable and significantly reduces the user effort and might make this feasible for use in practice as well. So to put it all together, our encoding of a system C design in PVL then looks like this in total. We have the encoding of the design with the threads that represent the processes and the data classes that represent the modules. We have the execution semantics for system C itself, including the scheduler and the event mechanism, as well as the global lock that ensures only one process can execute at a time. And then we have this reachable abstract states invariant, which as we call it, the RASI, which stores the states of all the processes and events in the design and is associated with the global lock so that we can use it for verification at the local level. To briefly also touch on how on our experimental results. We have conducted 3 case studies using this approach. 2 of them are relatively small. A simple robot that just detects if it's running into an obstacle and then is supposed to stop. A producer-consumer example that just sent data through a FIFO channel. And then also a larger case study of an automotive control system that includes an ABS or anti-lock braking system, which is a significantly bigger case study. And all these the case studies contain some program parameters, and about them we were able to verify both functional and global properties. So we are able to do both at the local level and also on the global level. As for verification time, you can see the small examples are really not a problem. They're both verified in under a minute, although the anti-lock braking system took about 3 hours for us to verify. So a significantly bigger system taking significantly more time. Although when we compare it to a local variant of the same case study, in which we only care about local properties, we see that almost all of this time is spent trying to verify the RASI and the global properties, which makes sense because this is the weakness of the deductive verification. However, also to put this into perspective, we also tried to verify this case study with 2 other approaches that already exist for System C verification based on model checking, and neither could verify this design at all. To briefly conclude, to summarize our contributions, we have developed a deductive verification approach for System C. We've written a tool to transform System C to PVL, and we've developed some techniques to verify also global properties which are not usually easy to do for deductive verification, including the RASI, a technique to reduce user effort. All of this is evaluated in our case studies, which seems to work well there, and we were able to show some advantages over other systems in dealing with both functional and also global properties, for instance, and showing a good scalability with regard to these unbounded program parameters and large data ranges. We were also found in our evaluation, though, some points for improvement. The manual effort is still relatively high, and if you look at our artifact, which you can find in our paper or through the QR code here on the right, you can see a detailed list of all the manual steps that are necessary. And we also need to look further at the RASI. However, considering the comparison with existing approaches, I still think our results are quite promising and that we can deal with these in future work. With this, I thank you for your attention and look forward to hearing your questions.
Thank you. Questions?
Wonderful work. Thank you very much. I had a question about that table of results, that very large time. Is that including the manual effort also? This is just the tool effort.
Yes.
So what do you think is causing all that time for verification? This is just running the solver, right?
Yes. So the majority of the time is spent trying to prove the RASI, which is quite large for this design, and also to prove the global properties.
But I mean, SMT, you're using some SMT solver.
Yes.
They can chew up these things. They can chew up very large VCs. Very fast.
Yes, but it is really, really large. It's so you see the number of states in the RASI there in the table. You also have to consider that is significantly larger than in the other case studies, of course, but it's also, because it has so many more processes and so many more events to include, the number of atomic conditions in the RASI is just off the charts. So that is what is the bottleneck at this moment.
Okay. One more quick question there. Maybe next speaker can prepare.
Hi, thank you very much for the talk. When we tried to do this, the problem we ran into was that System C really is C++, and parsing and doing semantic analysis and working on C++ is horrible. I wondered, did you have a smart way around that? Like, did you write a full C++ parser?
Disallow everything that is problematic.
Isn't that the whole language?
Oh, there's like plus operations are okay.
You say that.
And so we are working on a restricted subset of the system C that is possible. We don't allow TLM, for instance. We work on static designs, and then it is manageable.
Okay, and you do all your own parsing and
Yes.
semantic. Wow. You should have put a slide in about that, 'cause that's well impressive.
I was already a minute over time, so but thank you.
Okay. Thank you again.
Yeah, that's a little. Okay.
Okay, thank you. Next speaker is by Dwayne Burns from CMU, automatically enforcing Rust trait properties.
All right, hi, I'm Twain Burns. I use they, them pronouns, and I'm presenting joint work with Yoshiki Takashima and Lee Minjia at Carnegie Mellon University on automatically enforcing Rust trait properties. So the first question you might have is, what are Rust traits? These help define shared behavior abstractly. So if you've ever programmed in Java, they're very similar to interfaces. And Rust traits often have invariants. These are things that aren't checked by the Rust type checker, but still need to be true in order for the Rust trait to be valid. So for example, partial equality needs to be both transitive and symmetric. Just things that you would expect of a partial equality relation. These traits are often already implemented for the standard library types, but for user-defined types, it's often nice to be able to implement these yourself. So for example, if I had a custom type called object ID that has, say, an ID field that's just a length 12 U8 array, that's this right here, then I might want to implement the from trait. And so the from trait just converts from one type into another, and its invariant is that it's not allowed to crash. So in this case, we just take in our U8 array of size 12, and we just put it into that ID field. This won't crash. This is a valid implementation of from. So the problem that we run into is in formally verifying these trait properties. So we find that trait properties are often unchecked in a lot of real-world code, and when they are checked, it's usually through unit tests or fuzzing. And so we also wanted to increase access to formal verification. And so to go about this, we decided to encode some invariants as Rust assertions, and then use a Rust verification tool to verify these assertions. And just to make it all easier to use, we created a UI integrated with VS Code. So since we had to use just some Rust verification tool, we decided to use Connie. Connie is a bounded model checker for Rust. It verifies assertions for all inputs of a certain type, and it's best for bounded types, like U64s and I32s. So I thought I'd give just a brief example of a Connie test. So if we have some function called return even, takes in a U64, outputs a U64, does something, doesn't really matter, but we want it to always return an even number. We can write a Connie test for it that looks kind of like this, where we set some variable num to be of type U64 and just take on some arbitrary value. And then we assert that when we pass that number into return even, mod 2, it's going to be equivalent to 0. So just that return even will always return an even value. So our tool is able to support the following traits. So from and into, which just convert between types. It supports partial and total equality, partial and total orders, and asmut and asref, which convert between mutable instances and references. So here's a quick demo. It's just going to add a test for, on line 118, we have partial equality implementation for lim. which is just a custom data type in this library we were looking at. So if you just click the Add Trait Test button, and then when you save the document, you get a little play button that lets you run that Connie test. So as you can see, we have these first 3 lines here just set up our variables. The next line does the symmetry check, then the transitivity check, and then just another additional check to make sure there's consistency between not equal and not equal, and the other way around. And so then you get this little check mark showing that the test does actually hold. And explaining that took a lot longer than it did for the test to run, so we can see there's not a lot of overhead with this, which is really nice. So with this tool, we ran 42 harnesses on 6 popular rest traits. We found that the majority of the verification time was under 10 seconds per trait instance, so again, very low overhead. And we were able to find 3 issues in Prost, which is a protocol buffer library with nearly 40 million downloads. So one of the bugs that we found was a potential multiplication overflow in converting between custom types storing the date. And so there was this year to seconds function that on line 3 here, obviously I skipped a bunch of stuff, but we're doing some multiplication by 31 million something. And Connie returns that, I'm not even gonna try to say that number, but if you try to convert from that year into a different year, you might have a multiplication overflow. And obviously this is not a real year that we would see when we were trying to use this function, but it is potentially exploitable. So for future work for this, we would like to create transitivity for partial equality and partial order across more than 2 types. Within a specific instantiation of either of these, you can only have, you can only declare it between 2 types. And this tool currently only looks at 1 instantiation at a time, but if you declare it for 3 or more types across multiple instantiations, it needs to be transitive across all of them. And also, our tool is limited by the capabilities of Connie. So Connie currently has problems with performance on large crates. With polymorphic types, it needs a specific instance, and it has issues with concurrency as well. So all in all, our tool helps make formal verification for trait invariance available to all Rust programmers with no formal verification experience required. You saw, just click a button, adds the test, click another button to run that. And it's enabled by our fully automated harness generation tool. And if you want the GitHub, that's just at the QR code there. Cool.
Thank you. Questions? Yes, on the back, 2 questions.
Does Connie handle unsafe Rust? And if not, do you know, is it common for these trait implementations to use unsafe Rust, or is that more or less a non-issue?
Yeah, so I'm pretty sure that Connie is able to work on unsafe Rust. There are some traits that can be used unsafely. The crates that we were looking at, it was all within safe Rust, but we were looking to expand to that.
Can you talk about the user experience of diagnostics? So when there's a failure, what information is presented to the programmer, and does it seem to be sufficient in your experience of that, like people can take that information and solve the problem, or are there things to be solved in helping people understand this this kind of feedback loop?
Yeah, definitely. So I mean, if you ask for it, Connie can give you an example of a bad number, which doesn't necessarily tell you exactly how to fix the problem. It does say specifically, you have a multiplication overflow on line this, you know, with whatever value, like this one. And so, I mean, I think that's nice.
Does it also localize in the proof, I assume? Like, you have this big proof statement, and it says, like, oh, like, it's this specific assertion.
Yeah.
These sets of inputs, right? Okay.
Yeah.
Got it. Thanks.
Another question, final one?
Within a trait for equality, for example, you use the equalities of underlying types. Does the model checker like unfold all of that, or is it assuming the equalities used of included types are correct?
Yeah, so Connie will verify that even a standard implementation, like an implementation already within the REST library, Connie can verify that that actually does follow the invariance. So if you asked it to verify, so if we take this test here, and if we just put partially Q, and instead of A of type lim be Connie any, ABC of type lim, if we just set that to like I64, then it'll verify that it does follow these invariants.
But is it rechecking essentially stuff we should have already checked somewhere else? Like, is it?
I mean, it is potentially rechecking stuff. I don't know that I would say that it should have been already checked. Yeah.
Okay, thank you again. We can have coffee and meet here at 11.
One day, only because I go also to courses, and I did not want to pay 2 times because it's per day. I don't think you would say
Should be on now. Okay, it is on. Okay, so hello everybody. So we are now going to have the abstract interpretation session of VMCAI. So we are now, we have reached the AI part of VMCAI. So, and the first talk is about formal runtime error detection during development in the automotive industry. So this is joint work with Jesko Heking-Harbusch, Rochen Quante, and Maximilian Schlund. And Jesko is going Jesko is going to give the talk.
Yeah, so thanks for the nice introduction and welcome to my talk. So my colleagues and I, we are from the corporate research division of Bosch. And you may or may not know our company from our consumer-facing brands. So here on the right side, we sell kitchen appliances, ovens, drills, stuff like that. But originally, and still mainly, we are also an automotive supplier. So in a lot of cars, you can find these boxes, which we produce. And these boxes are embedded systems, so they combine some software with some hardware parts. And as you see with these examples of an airbag controller or an engine control unit for a motorbike, it's very important that they behave in a safe manner. And this we call functional safety. And when you all know use cars, you just assume that it works. So we have achieved, or we do achieve functional safety. And one of the reasons is that we have very involved processes and standards how to ensure functional safety. And one of the recommended steps is to use abstract interpretation to prevent runtime errors. And I think it is a very good idea to do so because yeah, your airbag should not crash due to an error out of bounds exception in the inopportune moment where you need it. And that's our overall goal that we try to achieve. But yeah, we face some challenges. So our code bases get larger and larger. So the C and C++ code we analyze becomes more and more because yeah, a huge part of cars today consists of code, and we only apply abstract interpretation in very late stages of development. So only in the very end, when everything is developed successfully and then plugged together, we get feedback from abstract interpretation, and this is often too late for the developers because they moved on or forget what they have forgot the details they have been working on. And we use a solution to solve these issues, which is to apply abstract interpretation on a module level. So instead of putting the entire code into the abstract interpretation engine, we split it up into individual modules. And at the intersection of these modules, we use contracts to maintain information that is needed between the modules. And this solves the problems we have been facing because, by analyzing individual modules, we become more scalable because we give less or fewer smaller chunks of code to the abstract interpretation engine, and the contracts help us to stay precise because they provide further information than just the syntactic data types between the modules. And our developers have also the benefit that they now can just analyze an individual module and get feedback while they're developing. And in the main technical part of the talk, I want to give more details how we achieved this. So we built a framework given here in blue with which our developers interact. So from their point of view, not much has changed. They just give their code to our framework instead of an abstract interpretation engine, and then they get an output that helps them. And our framework uses under the hood the external abstract interpretation tool Astray. We could also use other tools, but yeah, we have a lot of good experiences with this tool. And the main technical parts of the framework are these two steps. So one, generating a verification harness, meaning going from the incomplete or from one module to some code that Astray can analyze, and also some automation to obtain contracts because for legacy code or for large code bases, it is infeasible to write them all by hand. And now we will look into more details for these two steps. So generating a verification harness means, on a very high level, you get a module, and this module does not have a main function because the other parts of the code are missing, and then you have maybe contracts, and you want to obtain code that Astray can analyze. And we basically do 3 steps. So first we do some dependency analysis, which is similar to a compiler, just finding out what is there, what is missing. For the missing stuff, we need to generate stubs, which are just, which just for not yet implemented functions tell Astray how to handle them. And then we generate a verification driver, which actually uses the code in our module. And from these steps, 3 steps, we directly get the code which we give to Astray from the previous picture, where we just only copy the code of the module under analysis in the middle. And next, I want to give an example how our verification drivers usually look like. So imagine you have a small module which has one global variable, an initialization function, and two public functions which are callable from other modules. And then our verification driver looks like this. So in the beginning, we initialize the global variable, and here we use Astray-specific instructions, which in this case set the abstract state of the global variable to full range. Then we call the initialization function, and down here we have a while true loop that simulates the continuous or the behavior of an embedded system, and just has a decision variable, which again is also set to full range, and then simulates all orders in which these functions could be called. And for each function, we have one case. For the first function, the case is very easy because it does not take any parameters and does not produce a result. So we just call it. And in the second case, we need to initialize the parameters of the function, and then we also get a result. And now here you see a lot of full ranges, which probably makes analysis imprecise. And that's where our contracts come into play. So the idea behind contracts is to get more detailed information at positions where otherwise we would need to use full range. And I will illustrate the contracts we support by examples. So the first one are very similar to the ones we saw in the previous talk. And you can just specify preconditions and postconditions for functions. So for example, for a square root function, it makes a lot of sense to say that it only works on positive values and only returns positive values. Then in C and C++, arrays are often represented by pointers. So we need some kind of contract to say that we are dealing with arrays. So here we compare two chunks of memory, and we can say that pointer 1 and pointer 2 are representing arrays of a certain length. We have invariants for our global variables. And the last type is we can say which functions are part of the initialization of our verification driver and which are called cyclically in the while loop. And now we will see the benefits of the contract. So for the example of the square root function, it, on the one hand, can give us a better stub if it's not implemented yet, where you can directly see how the precondition becomes an assert, which is checked on the input, and then we generate a corresponding output to the postcondition. And when the function is under test in our verification driver, then it is the other way around. So here we only give the appropriate parameters according to the precondition to the function, and then we check that the output fulfills the contract. And this way we also find out when a developer writes a contract by hand and it is not fulfilled. About the contract inference, I don't want to go into details, but refer you to the paper, or I don't want to get into the deep technical details and just explain it on a high level. So here on the left side, we have some external informations which we can just directly parse into contracts. And here we use contracts from results of previous runs of the abstract interpretation tool. So this means, we can find out how functions are used and actually use that for our contracts. We implemented all of that and used it on real code. So here is a very condensed version of the table from the paper, where we have 3 subsystems from a driver assistance domain, braking domain, and cruise control domain. And I only depicted the, what is with 0, I depict when the entire system is given to the abstract interpretation tool, and with 1, I depict our approach. And you can see here that our approach finds fewer alarms, meaning that it automatically removes false alarms, which otherwise would be needed to be looked at by people by hand. And at the same time, we reach a higher code coverage. So yeah, we were very happy with these results, and therefore, okay, this should not happen. Oh, you don't see it, okay. Sorry. Yeah, kind of being successful on our internal benchmarks, we gave it to actual running programs, to actual running development projects. And yeah, here is some embedded control software having 2 million of lines of code in 3,000 C files. And yeah, with the low precision settings, they before us needed 3 days to analyze this. With high precision settings, I guess they aborted a run after several weeks. And we could reduce this to 12 hours when you add up the runtime for every module. And with parallelization, we could further improve this. And also the developers can now get feedback early during development and not in late stages as before. And the second real project we looked at was an embedded software library, which is a bit smaller. And here we have modules of 10 to 50 compilation units. And here we reach a very high code coverage of over 90%. And we find about 10 to 100 alarms per module. And all of these alarms have very short call stacks, because you can directly follow our verification driver to find out where problems occur. And this means that 10% of these alarms result in code changes, which is for our domain a very, very high number. So normally less than 1% of alarms would result in any code changes. And now you might think that this is a very buggy software, but in fact, this is not the case, but it's a library. And our tool or our framework is very good at finding cases where checks are not performed properly, because we call every function in all these orders, and we will always find out cases where people don't do any checks that they need to do, and only other people intuitively use it in the right way. And yeah, we got feedback from the developers. So one thing is they just expect that our formal methods tools are centrally available and as automated as possible. So they don't want to do manual steps. They found our contracts intuitive because, yeah, I guess I showed you the examples and you all pretty much understood them. And they also, or we achieved kind of a sweet spot in terms of our contracts, in terms of expressiveness for most cases and being easy to check. So stuff we cannot express is, for example, in an array, you could have the property that consecutive elements are always different, and this, yeah, you can't express with our contracts. The early feedback was greatly appreciated because, yeah, developers kind of found out that it's not some kind of certification step in the very beginning, but in the very end of the development cycle, but can actually give useful insights into their code. So to conclude, I showed to you how large code bases in the automotive industry are analyzed by abstract interpretation early during development. The tool or the technique we used is module level abstraction with contracts, which is illustrated by this picture. And we had very positive feedback, and the rollout to more projects is planned. So thanks for your attention, and now I'm happy to answer questions.
Okay, thanks, Jesko, for the very interesting presentation. So, how about questions? Patrick? And then David?
You told us what the developers liked. You did not told us what they don't like.
I mean, yeah. I mean, they don't like long run times. They don't like a lot of false alarms. Some probably would also prefer to not deal with abstract interpretation at all. Yeah.
There is no bug if you don't know.
Exactly. Yeah. Yeah.
David?
Hi, thanks for the talk. So you mentioned that you do not reach 100% code coverage. So what does it mean? Because you use another approximating static analyzer. So what does it mean?
Yeah, I guess that parts of the code are really not used at all and should not be there.
Dead code. It is dead code. You think it is dead code and.
I mean, it is some kind of dead code that probably, yeah, dead code searcher does not find. But because I assume they would look for that. But yeah.
I mean, another possibility is that you could have code that is behind some alarm where traces are cut. Like for instance, if you have some pointer error, Astray cannot quite make a state after that, so that could be the problem too.
Yeah,
so.
Precisely. So I mean, I showed, yeah. We also encounter definite alarms, as Astray is calling them, and we tell them they need to get rid of them before the results are meaningful. So, yeah.
Okay, so one more. And in the meantime, I will have one while you give the mic. Did you look into relational specifications where you try to say if the function is called with an argument that satisfies this, you get some results that satisfy some other property?
We did
Input,
not,
output.
We did not. But
okay. Is it relevant? Or,
I mean, it's so from my perspective, everything making our contracts or specifications more expressive is relevant. But we need people to write these specifications in some way, and this is the difficult.
Thank you.
When you said that 10% of your alarms resulted in code changes, does that mean that the other 90% were false positive, or just that the developers didn't want to make a change?
Both. So.
And yet, do you have an estimate on?
I have not.
How many?
I have not. But like, yeah, we can always argue why we don't do something because of an alarm.
So one related question, and then I let Patrick ask one, or go ahead.
When you have people that do tests, they need more or less to know what is the test going to check. And that's very similar to writing a contract, in fact. And do you have people that do both test and contract and use both abstract interpretation and test on the same contract?
Right now we do not, but like, yeah, it would be a very interesting direction. And like, I mean, we have also people dedicated to applying abstract interpretation, and they oftentimes then write the contracts. And these people can be different from the developers. And then they add contracts which help everybody using the code, because the analysis gets more precise. Yeah.
Okay, so while I think we are going to move shortly to the next talk, I had a sidetrack question to the last one. So you mentioned 10% code change. Is there a percentage of specification change where people believe something on the program and changed their belief after the analysis, which could also be very interesting to report?
Yeah, I don't have any numbers, unfortunately, but I agree that this would be very interesting. Yes.
Okay, thanks again.
Thank you.
So we are now going to the second talk, which is about abstract interpretation-based feature importance for support vector machines. And this is work by Abhinandan Pal, Francesco Ranzato, Caterina Oban, and Marco Zanella. And Pal is going to give the talk. So is it working? It is. Perfect.
Okay. Hi, so in this talk we are going to discuss about abstract interpretation based feature importance for support vector machine, and this is work done by me, Abhinandan Pal, Francesco Ranzato, Katrina Urban, and Marco Zinella. So let's for a moment imagine we do not live in Paris or London and New York, and we have an option while getting apartments. So we would consider various different numeric factors like area of the flat, the crime rate in the neighborhood, the bathroom counts, and the bedroom counts. And based on this, we'll come to a conclusion. Is the flat acceptable to us or is it not? And if someone were to ask us what are our priorities, how are we taking the decision, we would probably say something like, well, for me, the crime rate is the most important, then the bedroom count, then the area, and then the bathroom. And now, if you were to delegate this task to a machine learning model, like a support vector machine, well, it would still be able to say if you wanted a flat or not. But can it give me a similar way of reasoning to why it came to the conclusion? Well, yes, and it's a solved problem, and we are presenting yet another method to do it. So, why would you care? Line, which is one of the most common tools to solve this problem, is highly trusted by the machine learning community, which is evident from the 15,000 citations it has. And the table above shows that our method is extremely close to line, which means that our method can be used exchangeably with line. There is another tool called PFI, which varies from line on a few properties, and it has 1,000 citation of its own. And here we show that our method is closer to a baseline than compared to PFI. So we essentially have a method that is slightly better than PFI and is as good as line. So again, why would you care? People can just continue using line. Well, the reason is the time comparison. So if you wanted to get the ranking of the whole neighborhood, PFI would take 10 to the power 4 seconds for the adult data set for linear support vector machines. Line, on the other hand, for the neighborhood of 1 point, it would take 3.78 seconds. But if you wanted the ranking of the whole input space, we would have to get a data set, and the adult data set has around 10 to the power 4 points. So we would do the local ranking for each of the point and then take an average, meaning the time would become 3.78 into 10 to the power 4. But our method, AFI, takes 0.27 seconds for a local ranking of a neighborhood and a global ranking, making us 10 to the power 5 times faster. To understand that number, if we have this support vector machine, it takes around 2 to 3 hours to train, and then it would take Lime or PFI, again 2 or 3 hours to verify for explainability, which means that machine learning developers would not want to do explainability and would just want to skip that, which is sort of dangerous. But with our method, it's very much more feasible because it's a fraction of a second. Another interpretation of what the number 10 to the power 5 means. So if I was to start a line task at the beginning of the abstract interpretation session, it would be at the end of the abstract interpretation session that the task would finish. But our method takes as much time as doing this. So we have a fast and a formal method for feature ranking, and we also do fairness analysis. And if it is not obvious, I love iterations. So now, coming to a few key terms. First is local, which means the ranking is for the neighborhood of a point. Then global, which means the ranking is for the whole input space. Then we have model agnostic, which means the ranking can be used for any kind of machine learning model. Model specific means it is specific to a particular kind of machine learning model. For our case, AFI is specific to support vector machine, and it can be used for both local and global rankings. Line is model agnostic, so it can be used for any machine learning models, and it is defined as a local metric, but you can use it as a global metric by taking an average of local ranks. PFI is model agnostic, and by default is a global metric. So what are the advantages of our method over the others? First of all is the significant speed ups. Second is the fact that the local and the global method take around the same time. Next, we are deterministic method, whereas PFI is not deterministic, which means that you have to run it 5 or 6 times and then take an average. Ours is based on a formal method, whereas the others are a machine learning based heuristic. Next, we can handle correlation between features, which is something that PFI cannot do, and it's very common in machine learning data sets. Next, which is another important advantage is that we are dataset independent, which means that PFI and Lime requires you to have a dataset to do the ranking, which means you need time to collect the additional data, plus if there are any biases in the data, that biases will be present also in the ranking. But in our case, we do not have this disadvantage. Then PFI, which we are comparing with, the quality of the ranking is dependent on the accuracy of the model, which is not the case for us. So a quick overview of what a support vector machine is. Let's say we have a point Z, which we want to classify either as plus or minus. So we pass it through this equation. Here we loop across the whole data set, and for each point in the data set, we pass the point we want to classify and the point in the data set through the kernel function. This takes two vectors of same size and returns a scalar, which we multiply with the label of the point in the data set, and then multiply with the weight for the associated point, and then we sum across all points in the data set, and then we subtract with a bias term. So here this Wi and B are the learning parameters, and for most of the points the Wi are 0, and for those that are not are the support vectors. For the kernel function there are different flavors. There is the linear, the polynomial, and the RBF. The linear is basically a dot product. Polynomial has polynomial operations. RBF has exponential operations. And for linear support vector machines, we can represent it in a much more trivial way by in the primal form, because it is a line in the space partitioning to the plus side and the minus side. So it can be represented using a linear equation where we dot product the weights with the input and then subtract B. So the linear support vector machine can be expressed as a linear equation like this. Let's take an instance of this equation. So here if we wanted to do a ranking, so if we change the value of x4 by 0.1 and do not change anything else, the value of y changes by 0.07. If we change the value of x2 by 0.1, the value of y changes by 0.03. So we can say x4 is more important than x2 because the same change in it will cause greater change than in x2. So we can get a ranking that x4 is the most important, then x1, then x3, and then x2. And this is basically the orders of their coefficients. And this is comparable to doing a partial derivative, because if we do a partial derivative of this equation on x4, we would get 0.7. If we did it on x2, we would get 0.3. So the case for linear support vector machine was quite trivial, but for polynomial and RBF support vector machine, they are non-linear. So we cannot represent them in this trivial form. So, and doing a partial derivative, though possible, would be computationally expensive. So we try something else, which is abstract interpretation. So here, in regards to machine learning verification, we are given an input point, a support vector machine will give you an output label. But with abstract interpretation, we can consider a whole input space and use an abstract transformer for the support vector machine to get an over approximation of the output labels. And this input neighborhoods are represented using abstract domain, like the RAF abstract domain. Here, we have the input as the RAF input, then we use a RAF compatible abstract transformer for support vector machines, and we get an output RAF. And RAFs are represented with an equation like in this form, where A0 is the middle term of the abstraction, and for each of the features, we have an epsilon I and an AI term. So for the first feature, it's in this direction. This leads to a value of minus A1 to plus A1. The second feature allows for values is in this direction by epsilon 2, and it allows values from minus A2 to plus A2. So this allows us to create a hyperrectangle input with the different features. If there were 5, 6 features, it would be a bigger dimensional. And then once we pass it through the RAF transformer for a nonlinear support vector machine, there will be nonlinear operations which all will be accumulated using the AR epsilon R term and leading to the output having an extra dimension. So now we have taken the output of the RAF here in this equation, and now we will use this to get the ranking. Here A0 is shared across all the features, and thus we can ignore it. And the amount each of the feature contributes to AR is directly proportionate to their AI terms. So as the AI terms are still there in the equation, we can ignore this. This leaves us with an equation of this form, which is exactly the primal form that we saw before. And we can now use the trivial case again and get the ranking by taking the absolute value of the coefficients. And so now, if you are considering the neighborhood of a point, we would use the RF input as the neighborhood of that point, and we would get the RF output corresponding to the neighborhood, and thus the ranking would be corresponding to the neighborhood, and thus a local ranking. If we give the whole input space as the RAF input, we get the RAF output which corresponds to the whole input space, and thus the ranking would be for the whole input space. Thus we get a global ranking. So we can get local ranking and global ranking just by changing the values of this AI. But the number of computations remains same, thus they take the same amount of time to compute. So the abstract transformer that we used was Saver, which was introduced by two of my co-authors at SAS 2019. We made a few improvements to it and used it for feature analysis. The first improvement we made was the one-hot abstraction. So in machine learning, there is something called the one-hot encoding, but only one feature can be 1 and all others will be 0. Previously, they had just taken an interval of 0, 1 for each of the feature. Now we explicitly implemented this constraint and integrated it with the interval and RF abstract domain and proved its soundness. We then use the improved version of Saver to do fairness analysis on popular data sets, and then we also did counterexample search, which basically means if we have a point with a plus label and using abstract interpretation, we find out that in the neighborhood there can be both plus label and minus label points. Using a counterexample search, we would try to find those minus labels. So the part with feature importance is like 25% of the paper, and this is the rest 75. I gave a very big overview of this. For details, you can look into the paper, and I'll jump into the experiments. So for the fairness bounds, so now instead of giving a fairness score, which would be sound and complete, we try to give it a bound. So here we get the lower bound by using abstract interpretation, which is sound and complete, sound but not complete, which means if something is said to be fair, which is on this side, is definitely fair. But if it says something is not fair, it may or may not be fair. And then we do a counterexample search. So if counterexample search finds a counterexample, then it's definitely not fair because we have a counterexample. But if it is unable to find a counterexample, then it may or may not be fair. So we have an upper bound and a lower bound. Sorry, a lower bound and an upper bound. And if both the numbers are equal, then our method is technically sound and complete, which is the case for linear support vector machine. For RBF support vector machine, the gap is quite narrow, which is reasonable. And the actual fairness score would lie somewhere in between. For polynomial support vector machine, the gap is quite big. It's around 0% for the lower bound, and for the upper bounds it's 90. So we're basically not really giving any information. And these are percentages. And this is because the polynomial support vector machine has polynomial operations, and the abstract transformers for them are not very precise, but in future we would look into try to building more precise ways of handling it. Now, so in the first few slides I was talking about distances between the different ranking methods. So this is what I meant. So let's say we have the German data set and we have the different features of it arranged in the same order. So the baseline gives different scores to the features based on their importance. And then the AFI gives the scores and PFI gives the scores. And we compute the Euclidean distance between the two. So here there's only 1 point of difference. So the Euclidean distance is 1.0. Here between these two, the Euclidean distance is 3.16. So we are much closer to the baseline as compared to PFI. That is also the case for RBF support vector machines, where we are 1.73, they are 4.24. For polynomial support vector machines, we are still closer, but the numbers are pretty big. And if you look into the numbers, it's kind of like random order. So why are we not doing well for polynomial support vector machines? Well, as I showed you, our abstract transformers were not very precise for polynomial support vector machine. So in future, if we or someone else finds a better way to handle polynomial support vector machine, the ranking will also improve directly. So in this table, I have considered different hyperparameters for the baseline and the other data set. This shows that our closeness towards the baseline generalizes across different data sets and hyperparameters. Next, here for the local rankings, instead of building another baseline, we just, as Lime is widely used, we showed that our method is extremely close to Lime when we set a high enough size of epsilon, which is the size of the neighborhood. And finally, about the time comparison again. So for the adult data set, the speed up is around 10 to the power 5 because the data set has around 10 to the power 5 points. For compass, it's around 10 to the power 4. For German, it's around 10 to the power 2. In general, the bigger the data set, the faster we get. And the amount of time difference we have across different variants of the supported machine is less as compared to the other methods. So thank you, and I would conclude by thanking my co-authors and the anonymous reviewers and people who saw the presentation before I presented and gave a lot of comments. Thanks.
So we have some time for questions. Patrick?
How is received your work in the world of artificial intelligence and things like that?
Honest answer, we submitted thrice and they said too much math. So, I mean, to be honest, the first version of the paper we had didn't compare it with Lime because we did not know which were the important ones. Later on, we understood what were experiments that would convince them that the tool is good enough, but there was always the problem that the math was too mathy. And there is a 6-7 page limit, and half of our paper was in the appendix. So here we have a better page limit, and it makes more sense to it's more understandable.
Okay.
That's what I was expecting.
Yeah, Lime and PFI are very trivial, and I mean, it's literally taught in advanced AI classes.
One question regarding to your abstract states. Looking at the formulas you did show, I was thinking about zonotopes. Did you look into the zonotope abstraction?
Yeah, so it's comparable to zonotop, but zonotop has multiple, like every layer adds variables. In support vector machines, it's technically one equation, so it's like one layer, so it adds one. So it's technically like a special case of zonotop. Yeah. So it's like a special case of zonotop, we could say.
Okay. Any other question? Yeah.
So is it possible to apply your approach to explain deep neural networks?
So this is what I was talking to my advisor 2 days back, and we will try to do that. There are challenges. One main challenge is the fact that here we had only like one, so we had only one nonlinear term, but when for neural networks, we would have to consider something like zonotop, and there would be a lot more number of nonlinear terms. And we manually proved that this nonlinear term can be ignored. But I'm not sure if in case of neural networks, can they be ignored? If they can be ignored, this method extends, but it would probably be like a few months of more research.
But you know, so there are some existing works that apply abstract interpretation to robustness verification of deep neural network. I think so. There are some quite related.
Yeah. So I mean, so our work, like one of our contributions was the fairness analysis of neural networks. So that's where the project started, and later on we moved into trying to get the ranking. So our paper does cover those things also.
Okay, thank you. So I think we are going to thank the speaker. And, okay, so the third presentation of the session is about generation of violation witnesses by under-approximation abstract interpretation. So this is work by Marco Milanese and Antoine Minet, and Marco is going to give the talk.
Okay, thank you for the introduction. So in this presentation, I would like to present some work I did in collaboration with my supervisor, Antoine Minet. And this is about a backward analysis with abstract interpretation for finding under-approximations. So this is the outline of the presentation. We want to do a brief introduction, then I will show the main contribution of our work, and then I will discuss a bit about implementation and results. So as we know, abstract interpretation is sound by construction, meaning that we always know that the abstract interpretation of a program S will always compute an over-approximation of the concrete interpretation of the same program. And unfortunately, this means that we can also have this issue of false alarms, which means that a program S may be correct with respect to some specification, but the abstract interpretation may fail to prove that this is the case. And in practice, this occurs a lot, and that is why we want to have a way to classify alarms in some way. So an approach for this would be to look for counterexamples for alarms in general, and this is what we can do, for example, with some model checking methods, also by symbol execution or incorrectness logic. Unfortunately, most of those methods, and they often are limited in terms of scalability, because, for example, they handle loops by unrolling, or methods such as symbol execution may have problems with an exploding, so a very big number of paths, and so again, this can trigger some scalability issues. On the other hand, abstract interpretation can handle these issues because, for example, we handle loops by widening operators. So to show what we would like to do with this analysis, I have a short example. In this simple program, we have two variables, I and j, and an array of 3 elements. So this loop here, in this loop, at each iteration, we non-deterministically increment j or leave it unmodified, and at the end, we access the array with the with the value of j. So, conventional analysis by abstract interpretation will find out that j is between 0 and 15. But, and so again, we have an alarm at this location here because we may overflow the array. And so we want to have our background analysis here and find out whether this is a true alarm or not. So we start with the condition that makes this a true alarm, so j between 3 and 15. And then we go backward in our program looking for preconditions that actually make this alarm a true alarm. So when we analyze the loop, we want to be sure that no matter the non-deterministic choice we take here, so whether we increment or not j, we always find some precondition that will be such that if we reach this location here, j will be in this bound. And so the output for this is that the input must be between 3 and 10, because in this case, if this is the case, no matter the non-deterministic choice here in the loop, we'll always reach this location and make j be in this interval. But I would also like to remark that an under approximation of this interval here is also a valid precondition for us. For example, you can take 4, 6, any input in 4, 6, and still you get a condition that if it will reach this location here, j is in this interval again, so again the alarm is a true alarm. So to summarize, the kind of precondition we want to compute are sound for under approximations rather than over approximations like we do usually in abstract interpretation. We want them to be independent from non-determinism, meaning that no matter the non-deterministic choice you take in the program execution, we always, if you reach the alarm location, you make it fail. And we want to find those conditions by abstract interpretation. So fortunately, this analysis was already presented in some previous work by Antoine Minet, in particular in this paper about under sufficient precondition analysis. And this analysis computes a sort of abstract interpretation equivalent of the Dijkstra's weakest liberal precondition, but with non-determinism. I want just to show a bit how does this thing work. So let's assume the simple while language with only numerical variables and those 3 statements. So this analysis works by induction on the syntax. So if you want to, for example, analyze the program made of the composition of 2 subprograms, you just perform the backward analysis of the second program first, and then the first program. For if then else blocks, you first analyze the 2 blocks, the guards, and then you perform the intersection of the 2 results. While loops are handled by greatest fixed point instead of least fixed point. And finally, for the atomic statements that for this simple language are only assignments and guards, we have some direct formulas to compute the results. And I also want to remark that for the Boolean filtering, we have a union operator here. And we will use this later. Okay, so this work was mostly in a seminal work. And of course, it has many limitations where we want to apply it for real-world C programs. For example, there is this union operator that we have just seen. And unfortunately, it's not easy to compute the union with abstract domain because we need to have an under approximation, so we cannot use the join operator because that will compute an over approximation. There is no support for program inputs. I will say a bit more what do we mean with program inputs. The original work was assuming as integer semantic where you really have mathematical integers, while in C programs you have integers with a finite precision. There was no support for arrays and memory, and also there was only support for polyhedra domain, and maybe you want to have some more powerful domains or even partitioning techniques. So there's a lot of work on doing this for this. So of course, in this work, we haven't tackled all those issues. We mostly focused on union, program inputs, and integer semantic. So to show what I mean by program input, I want to start with this by comparing those two very simple programs. So in the first program, we have this input command, which we assume will be getting some input value from an external user. And so in some sense, the result of this statement is, we assume it to be controlled by the user. Whereas the run command on the right is some non-deterministic choice embedded in a transition system. So we assume it not to be controllable by the user. So the original work was only supporting this kind of non-determinism and not the input. And so in order to add support for those input statements, we extended the language, and we try to provide a semantic also for this command. So our approach is to augment the state that beforehand was just a map from variables to their corresponding values. And now we had also we had support with we had some streams that will represent the inputs from the user, and the semantic of this input command. So a stream is just an infinite sequence of integers for us, like this. And whenever we execute an input statement, we are just reading one value and putting it into the variable and moving a pointer in the stream by one. In order to have an abstraction of this, because we want to handle this want to make this an abstract domain for this, we take a very simple case where the stream is repeating always the same value. And this is very convenient because we can reuse some conventional numerical domains and encode this stream simply as a numerical variable. Then there is the problem of union. So in the original work, it was mostly focusing on the polyhedra, and so at a certain point you need to you need to compute the union of two polyhedra like this here. So while for over approximations you can perform the join, and so there is this result here. For under approximation, you can have multiple results. For example, you can take the triangle over there, but also the rectangle here. So there is in principle, there is no way to pick which of the two. And the original work was using some heuristic to guess which one of the two to use. Here we try to avoid to make these heuristic guesses, and so we relied on some power set construction where whenever you need to compute a union, you just merge the two sets of polyhedra. Again, you can also have MIT using power sets, and you can implement the transfer function as well by computing pointwise the transfer function on the power set. And then finally, we tackled the issue of integer wrapping. For this, since we are working mainly with polyhedra, we reduced some work that was already done on this. And in particular, this paper by Simon and King presents how you can implement, how you can analyze programs with integer, like C-like integer semantic, using the polyhedra domain. And in particular, they show that everything boils down to some wrapping operator that needs to be implemented in the polyhedra domain. And what this operator does is, for example, if you have a polyhedra like this, which is spanning multiple quadrants of the space, of the state space, what this operator does is it simply cuts the polyhedron in multiple parts and brings everything to the first quadrant. So this is the result. So for our backward analysis, we want to have a backward version of this wrapping operator. And so what we can do here is take all the polyhedra in the first quadrant and put them back in all the other quadrants. So this is the result we want to get. And to pick which of those polyhedra should be actually kept for the precondition, we can rely on a forward pass that already gives us an forward invariance, so an over approximation of the set of states that the program can actually reach. And so we already know which of those polyhedra are actually reachable. And so this is the way we can pick the correct polyhedra to keep. So all this work was implemented in a simple proof of concept analyzer consisting of roughly 10,000 of OCaml line. We tackled only numerical C programs, and we used mainly this polyhedra domain, and in particular with the power set version of it, so in general sets of polyhedra. In addition, we tried also to generate violation witnesses, as in the form of the SVComp witnesses. So those witnesses will show a program trace that can make the task fail, essentially. And critical piece is missing in our analysis for this. In particular, we don't have any way to check termination. And so for this, we took a very simple strategy. We try to inject the inputs that we have found during our analysis in the program. We compiled it and ran it, so we simply checked with a time limit whether the program terminates or not. And finally, the shape of the witness we used is simply resembling the control flow graph of the program. In order to assess the performance of our analyzer, we extracted some tasks from the SVComp, in particular from this set of the SV benchmarks. And of course, we took incorrect tasks. So this is the result of our analysis. Oh God, I'm sorry, the analyzer name came out. So on blue line is our analyzer. On the red is CPA checker. This is ultimate atomizer, and this is no, sorry. So this is our analyzer. This is CPA, ultimate atomizer, and this is variance. So those are three leading tools from the SVComp, and we try to compare their result with ours. So the blue line consists of the programs that are successfully analyzed. The red line consists of the programs for which we have an unknown result. The yellow line is the timeouts, and the black line is the black bar is the programs where we didn't support all the features, so we couldn't analyze. So as you can see, our analyzer is not performing very well compared to the other analyzers, but still we have many less timeouts. And in particular, I want to stress that we have a major performance increase compared to the other analyzer because we are using those, since we are using absent interpolation techniques, and so we can scale up more effectively. There are more benchmarks in the paper where you can also see this. So as a future work, we would like to be able to handle more features of C programs. So for example, we would like to have some way to analyze also programs consisting of arrays or structs, also dynamic memory allocations and so on. We would like to have more powerful numeric domains, such as intervals, congruencies, but also packing techniques to make polyhedra more scalable. Then we would like to have also less trivial input abstractions, so not just streams that always repeat the same values, but also maybe something more more advanced. And finally, we would like to have also partitioning techniques. So in conclusion, we have seen in this talk I present a bit about how you can compute sufficient preconditions. Then we've seen how we extending this analysis by adding support for some features that are very useful when you want to analyze C programs. And finally, we concluded with some experimental results. So with this, I would like to thank you for your attention and
Okay, thank you, Marco. So we have time for questions now. David Pichard.
Hi, nice talk. So you use a power set domain for your union.
Yes.
Do you bound the number of elements in your set for scalability?
Yes. So we do have a bound on number of elements, but we also have our refinement technique inside our power set. So during our analysis, and in some specific point, we try to merge or to combine the elements in the power set together. So we do have some kind of unions between polyhedra, but unlike the union that were performed using the heuristic. So again, we still need to have some heuristic to decide which parts of the polyhedra to merge, but we can do this in a later phase of the analysis, so we don't need to do it immediately, like when there is a union to compute. So this way we can keep a higher precision while still not having to keep too many elements in the power set. And if we cannot combine elements, there is always the option to drop polyhedra from the power set.
And a second question is, so as far as I understand, you have an alarm and you try to refine this alarm to understand if it is true alarm. For scalability reasons, is there a way to apply your technique on several alarms at the same time? Because
yeah, you can totally run. So our analysis works by computing preconditions for other alarms at the same time, but you can easily enable only a subset or only a specific alarm, multiple, so it's totally independent from that. But yeah, I mean, in the end, if you have multiple alarms at the same time, you don't know the precondition that you find, if they're preconditioned for a specific alarm or for other alarms. So that's the drawback.
Just one quick follow-up to the first question by David. Can you say a few words about how you do the merging? Like, how does this heuristic work? Like, if it is not too long to...
Okay, so there was already some work. So there was already some work on computing, on checking whether the union between polyhedra is exact or not, the join is exact or not, and we relied on that for relational polyhedra. But this doesn't prove to be sufficient when you want to have, when you have integer variables, because in those cases, even if the union of the rational polyhedra is not exact, maybe the integer one is exact, and so in this case we have a special algorithm for computing still the union.
Okay, thank you.
Would your technique be useful for necessary precondition?
No, because for that you need to have over approximation, so it.
Okay, so you think about it.
Okay. Okay.
Naim?
Yeah, I was just curious about what are the reasons the other tools are better, and is the input abstraction one reason of that?
The input abstraction? Sorry?
Yeah, is the input abstraction one reason of that?
No, I don't think it is. So unfortunately, the tasks from SVComp are more focused for model checkers, I would say, especially from this particular set. There are other sets where abstract interpreters can do a bit better, but for this particular set, I think it's not the best. I took these tasks because they were the simplest, like they consist of simple loops, but sometimes they contain, for example, congruencies, and it's not easy for our analysis that only supports polyhedra to handle those as well. Okay. So I think that's mainly the case, the issue.
Okay, so we will. Well, okay, we can take a last question and then move to the last talk.
So, hello. In SVComp, generating the witnesses is just half of the story. So you have a bunch of tools that actually are supposed to read those and then validate your claims. Have you tried those tools to see if they can actually validate your witness is showing that actually you are giving enough information for them to verify the claim?
Yeah, so the success bar for our analyzer consists only of tasks that were successfully validated by certain validators. So all of those were validated.
Okay, thank you very much. So we are going to move to the last talk of the session, which is on correctness witness validation by abstract interpretation. So this is work by Simo San, Michel Schwartz, Julian Erhardt, Helmut Seidel, Sarah Tischer, and Vishal Fojani, and Simo is going to give the talk.
Thank you for the introduction. So in the context of our work, witnesses are exchangeable proof artifacts for program analysis results. And as we saw, these can be for violations like counterexamples or for correctness. And our work focuses on correctness witnesses only. And one place they are used is SVComp, or the computational software verification. And there are witness validators, which are based on model checking, test execution, etc. But so far, the ones for correctness witnesses were all based on model checking. And the competition organizer, Dirk Baer, has in a recent report stated that there is a remarkable gap in software verification research because there are results that cannot be independently confirmed. Therefore, the goal of our work is to complement existing validators by developing a new abstract interpretation based correctness witness validator. So first, a couple of definitions. We assume there's some kind of program P, and the set N of its location and the set V of its variables. We also assume some kind of invariant language is being used, for example, C expressions, which are currently in SVComp, ACSL, something else. And with these definitions at hand, we can say that the correctness witness for a safety property of a program is this tuple where the W component is a mapping from program locations to their invariants. And some or many of these might be these trivially true invariants as well. And the note is that these location-based witnesses, they are simpler than the automaton-based ones that have been used in SVComp for a long time. Now, such a witness, it is valid if the program satisfies the property, and whenever the execution reaches any particular location in it, the invariant at that location should hold. And the witness validator then is a tool which attempts to prove that the witness is valid, so it is checking both of these conditions. However, SVComp has used a slightly weaker notion of witness validation, which we call witness-guided verification, where actually only the first point is being checked. But in that process, the tool might look at the witness invariants as some kind of hints or guidance. So quickly about abstract interpretation, we assume some kind of abstract domain D with all the usual suspects, widening and narrowing. We assume abstract semantics for the primitive statement, like assignments, assumes, and havocs, which non-deterministically assign a set of variables. And then an abstract interpreter combines these things, probably does some fixed point iteration, and gives us a mapping sigma from the locations to their computed abstract values. And now we can think about the witness validation again. So a witness is validated if this computed sigma is sufficient to show that the property holds for the program. And for every location, the invariant is true in all the concrete states corresponding to the computed abstract ones. But this requires a concretization, which is maybe not very practical. So a realistic tool might evaluate these invariants abstractly instead, which is less precise but still sound. However, as it is formulated here, witness validation is simply extra work for the abstract interpreter. It also has to check the second condition. But we would like somehow that we benefit from knowing the invariants ahead of time, which some other techniques already do. And for this, we study witness-guided verification in this first point, and we want to achieve three things simultaneously. So we want to use the invariants in the witness to somehow reach a fixed point, which is maybe more precise, or to reach it in fewer iterations. At the same time, we have to avoid overshooting the property that we want to prove about the program. And finally, we should not trust the invariants in the witness to be correct. And I will illustrate our technique with a small example. So first, here is there's no witness. We will just do normal interval analysis on this tiny program on the left. At the end of the first loop iteration, we first get there with the interval from 39 to 39. At the beginning of the second iteration, this is joined with the initial value. It's a loop head. We apply widening, and we lose the lower bound on this variable. And then we can do another iteration. We reach a fixed point. We can try doing narrowing there, but this won't help in this case. And we have no lower bound for this x. But now suppose we have a witness which gives us this invariant that x is between 0 and 40 at the loop head. How can the abstract interpreter benefit from knowing this? Well, in our technique, when we reach this loop head, Well, we first time reach it within this interval from 40 to 40, and what we want to do is to relax this abstract value according to this invariant expression that we were provided into a less precise one, in this case, the interval from 0 to 40, and then continue interpreting the program. And then we see that we reach a fixed point in a single iteration. And then we actually gain two benefits here. First, we managed to confirm a stronger invariant about this program that we could not infer from scratch, and we did so in fewer iterations of the abstract interpreter. And we might not always get both of these benefits. So to go more formal, we will now look at this relaxation step that we did there. And for this, when we are given a witness, we will insert into the program special unassumed statements with the invariants that were given by the witness. And the concrete semantics of these is that they are completely a no-op. The abstract one is, however, that we want to relax the states in a way which is somehow dual to the usual assume operation, which takes a less precise abstract state and, according to the expression, refines it into a more precise one. And our operation should go the other way, from this more precise thing with a different expression to the less precise one. And by choosing witness invariants suitably, we can give up this precision in a controlled manner and hopefully verify the program still. And now we will look at abstract operators corresponding to these unassumed statements. And we also have this sub v here indicating the set of variables we want to actually relax, which will somewhat simplify things. And what we want is that these operators be sound with respect to the no-op semantics. And if that is the case, then the entire abstract interpreter remains sound with respect to the original program as well. Now, because the concrete semantics is a no-op, we will specify the intended abstract behavior through a number of examples. So first, suppose we have an abstract state with many variables in it, but the invariant is only speaking about some of them. Then others should remain fixed in this operation. And this means that witness invariants are not required to describe complete program states at all program points, but they can only speak about the relevant variables at every point. The role of this set V is shown in the second example, where if the invariant has multiple variables in it, we might still want to keep some fixed and relax only the others. Now, things get a bit more interesting when we look at the relational abstractions. And there, let's think about the state where that describes that 0 is equal to x and x is leg of y. And now we want to relax this first equality into an inequality. Here's the same thing spelled out with octagon constraints, but the key here is that when we are relaxing this x and this first equality, then we want to preserve the inequality between x and y here. And finally, we would like these unassumed operators and the witness invariants to be able to leverage things that the abstract interpreter is already computing, for example, points to sets. And then this would allow us to provide witness invariants through the just pointers without having to explicitly state the points to sets also in the invariant. But this is particularly necessary for programs with dynamic memory allocation, where the only way to refer to these values is through the pointers. Now, one very naive way to define such an unassumed operator is to just havoc the variables we want to relax and assume instead the expression that we want. And to remain sound, we also join it with the incoming abstract value. And this works very nicely for the simple illustrative example that I went through before. But where it fails is exactly this relational example, because when we are havocing x, we immediately lose all the relations between x and anything else. So how can we alleviate this? We will make use of a dual narrowing operator, which, given two abstract values d1 and d2, returns something between them. And this gives us a scale to tune the precision of such operator. And what we do is we take the previous unassume and we wrap it with this unassume operator. And by choosing suitable dual narrowings, we can make the unassume do what we want in a suitable level of precision. And this succeeds for the relational example we have in the paper. Defined a specific instance of a dual narrowing for relational domains, which makes it work, and it exploits abstract domains with heterogeneous environments. So you have abstractions which use different sets of variables potentially overlapping, and how to, for example, join them together. But where it still fails is with pointers, because this abstract assume operation, it cannot refine things through ambiguous points to sets, but we would like to do that. And therefore, we look at a classic algorithm, HC for revise or backwards evaluation. It is commonly used to implement the abstract assume operation for non-relational domains in a syntax-driven manner. And it works very intuitively. You have an abstract state where maybe x is from 40 to infinity, and you want to refine it with this equality. We can think about this equality in abstract terms. We want this equality to evaluate to a definitely true Boolean in our abstractions. Then we can use the backwards operator for equality here to compute from the value of the entire expression, the value of its right argument, what should the value of its left argument be. And similarly, using the backwards operator for plus, compute what should the value of its left argument be again. And then we get a more refined value for this variable in this expression and can construct a more refined state. And this algorithm, it has essentially 3 phases. There's the bottom-up evaluation of the expression as usual. Then you have top-down propagation of the expected values of the sub-expressions. And finally, you can construct the resulting environment. And we can easily adapt this into an unassuming operator with quite minimal modifications. And this will work very similarly. Now we have a more precise state, and we want to relax this up to this kind of inequality. And we can leverage all the same backwards operators to compute possible values for x in this expression. And the important thing here is that here we should not refine this value of x that we find from the expression with a value of x that we currently have in the environment, because otherwise we will never be able to relax anything. Also to note here, we don't have this sub v here because this algorithm essentially chooses the set of variables to relax itself. And this is useful in some cases where a large invariant wants to relax multiple variables in the same expression, in the different sub-expressions of one big invariant, but they might also depend on each other. And we have examples of this in the paper. And to also note that this is not the same as taking the first naive definition and into the assume part of it, just plugging this propagating assume algorithm. And finally, I will just say that this generalizes nicely to the pointer example that we had before and a number of other examples that we provide in the paper. We also evaluate our approach. We do it in terms of precision and in terms of performance. And to do that, we implemented in the Goblin abstract interpretation framework some unassume operators. And for non-relational domains, we implemented the propagating unassume algorithm. And from this experience, we know that this indeed required minimal effort because we could reuse all the backwards operators that were already there. And for relational domains, we implemented the dual narrowing one that we describe in detail in the paper. So first, our precision evaluation, we use a set of examples from abstract interpretation literature, which require some maybe more advanced techniques to infer certain invariants. And the Goblin, it does not implement these techniques. It maybe solves some of them due to orthogonal reasons. But when we manually write witnesses with the right invariants for all of these programs, then Goblin, extended with our witness validation technique, which unassumes these invariants, it can validate all of these witnesses. So it verifies the programs, and it can also prove that the witness invariants themselves are all correct. So we see an improvement in precision on what it can infer and what it can actually confirm. And similarly, we use 2 SVCOM tools, CPA checker and Ultimate Automizer, to produce witnesses for these programs. For witnesses from Automizer, many of them are completely validated. In some cases, we failed to prove all the witness invariants correct, but we can verify the program, which we could not before. So in these yellow cases in this table, we have performed just the witness-guided verification. And this happened more often with witnesses from CPA checker on these programs, at least. And now about the performance evaluation. There we took a set of slightly larger programs, but they're not very big. But these have been used to evaluate Goblin in the past. And first, we just ran Goblin on them as is. We observe some runtimes, and we also have a look at the number of transfer function evaluations that are performed in the fixed point iteration process for these programs. Then we manually wrote the witnesses for these programs with some invariants in them. And we used our technique for witness-guided verification to, again, verify these programs. And what we see is that that the analysis goes both faster and also the number of transfer function evaluations goes down as we expect. So to finally conclude, we made 3 main contributions. We have specified the unassume operator. We have a general instance of it for relational domains that uses dual narrowings. We have an efficient algorithm for the non-relational domains, which generalizes also the pointer variables. And we have implemented these things also in the Goblin abstract interpretation framework. And from our practical evaluation, we see that this indeed, unassuming witness invariants in this manner, can make the analysis both faster and more precise. And thanks for your attention.
Okay, we have time for questions. Patrick?
It's more a comment than a question. It's a very interesting generalization of a trivial thing done in Astray. When you want to check something is an interval, you assume that it is in it and you iterate the fixed point, and then you do one more iteration, not assuming, and then if it's still included, it's okay, otherwise it's not. But in Astray, it's only for intervals, so the unassumed is kind of trivial. And I think it's very interesting generalization.
So regarding to the unassumed operator, all the examples you have shown in the talk are about intervals.
The technique itself is not specific to intervals.
Right.
I mean,
So
all
the
the non-relational things in Goblin as well, we have other non-relational numeric domains. They work for all of them.
So my question was about relational domains. Did you look into that?
In our implementation, we used Apron, so this works both for octagons and polyhedra. And for the precision examples, actually, many of them actually are polyhedral, and we use the.
Okay, so because the question I wanted to get at is that in such domains, you have also internal reduction that could reestablish some constraints. So did you have cases where essentially you have to, the unassumed statement is essentially fighting against the domain which re-adds the constraint that you want to unassume? Like I guess this is, like Patrick just mentioned Astray, and I think we had this in Astray at a long time in the past with bouncing effect. No? Patrick seems confused.
I don't recall if we saw that in any of the examples.
Okay, so maybe we can discuss this offline. David?
Maybe my question is related, I'm not sure, but the assume operator, as far as I understand, sometimes you can iterate it and you gain precision. And do you have a similar effect with the unassume operator?
Yes. So for this propagating algorithm, I mean the assume version of it, you can iterate locally to get things more precise, and actually you can do a very similar thing here. And instead of using you would use widenings also maybe there to get it to do the things. And indeed, if there are sub-expressions which depend on each other, for example, one of the sub-expressions is relaxing a points to set, and the other is relaxing variables through the points to set. They depend on each other. Then you would do doing it multiple iterations of this kind of algorithm will actually relax first the points to set and then everything through the points to set.
I have a similar question. I did not understand why it is 3. When you go back, you say up, down, up, or down, up, down, and it's stable, yes. Then why, I'm not sure, why is it 3 only? Why don't you need iterating?
I mean, you can iterate this. I just didn't mention it. It's just one instance of it.
Not optimal.
Okay, any other question? Okay, if not, we will thank Simo again, and I will. Any comment? Okay.
Welcome to the first session of this afternoon. The title of the session is Probabilistic and Quantum Programs in Neural Networks. And so we will start with a presentation by Luisa Collodi. And the title is Guaranteed Inference for Probabilistic Programs, a Parallelizable Small-Stack Operational Approach. Please.
My name is Luisa Collodi. I'm a PhD student from the University of Florence, and I will talk about guaranteed inference for probabilistic programs. This is a joint work with my supervisor, Michele Boreale. Okay, probabilistic programs are usual programs with the possibility to sample values from known probability distribution and the ability to condition the values that the output variables can take using external observations. And this second feature is very important because it allows us to incorporate external knowledge inside our programs. For instance, let's consider this small program here. It tosses 2 fair coins, and this is simulated as 2 draws from a Bernoulli distribution with mean 0.5. And the outcomes are saved into 2 variables, C1 and C2. At the end, we make an observed statement that blocks all the execution that do not satisfy the condition, C1 or C2. And in this sense, observed statement condition the values that the output variables of the program can take. Okay, essentially the meaning of a probabilistic program is given by the joint probability distribution of all its output variables, and there are many applications, for instance, speech recognition, computer vision, and so on. Okay, a probabilistic program implicitly defines a posterior probability distribution on all its output variables. It is called posterior because it is obtained using external observation. Probabilistic inference is the task of computing an explicit representation of this probability distribution. For instance, going back to the previous program, here we have this table that is an explicit representation of our posterior probability distribution. In fact, we have that the probability that that C1 is equals to 0 and C2 is equal to 0 is equals to 0 as a result of the observed statement that blocks all this execution. So, in general, unfortunately, probabilistic programs involve a large number of variables, and thus it could be very difficult to represent the posterior distribution as a table. And so we can use summary statistics in order to synthetically represent this distribution, such as the expected value, as we do here. Okay. With the aim to provide the semantics of our probabilistic programs, the denotational approach dating back to Cosen in 1978 is well established, and it represents the meaning of a program using a function, so a mathematical abstraction. And as you can see here, it is very elegant, but it does not translate immediately to an inference algorithm. Identifying the posterior distribution defined by probabilistic programs means making inference. And so we need some inference methods, and there are a lot of inference techniques that can be broadly classified as static inference, such as static and symbolic analysis, that are syntax-driven techniques. They give results with guarantees of correctness, but they have, in general, a limited applicability. Then there are dynamic inference techniques that run the probabilistic program several times and then look at the output variables in valid runs, so in all the execution that have not been blocked by the observed statement. In this case, they have a more universal applicability. And so we will focus on dynamic inference methods. However, also dynamic inference methods have some issues. For instance, it's not easy to deal with non-termination. Let us consider this while unbounded loop. It is a while loop, and it does not always terminate. So it is not easy compute or bound, for instance, the expected value of the variable p. In addition, there could be some performance issues, mainly considering execution times, that can affect approximate inference algorithms. Approximate inference algorithms may have some problems also with guarantees of correctness, because in general, for instance, Monte Carlo Markov chain, then do not provide formal guarantees of correctness because they are proved to be correct only asymptotically, but we will consider a finite number of samples. And this is because the samples that we are making using these methods are not independent, and so we cannot provide guarantees of correctness. Okay, thus we propose an action-based probabilistic programming language together with an operational semantics that is formalized as a Markov kernel and that directly leads to an exact sampling algorithm that can be single instruction multiple data parallelizable. On the top of the operational semantics, we also define an observational semantics in terms of expected values computed on infinite execution path. So this expected value cannot be directly computed, and thus we provide an approximation theorem that gives upper and lower bounds for this expectation for the exact observational semantics. And they only relying on finite execution path of the program. We have made some experiments using a proof of concept implementation based on TensorFlow, and the results are very encouraging, both in terms of correctness of computation, of accuracy of computational time. Okay. In order to formally present, describe a probabilistic programming language, we need to specify its syntax. In this case, we have that an action can be an assignment or a random extraction. Here, G is an update function, and big F is a density function. Then we have that statements can be represented using this grammar, not the present of fail, because our language contemplates failure in the sense as a result of the observed statement. In our case, we abbreviate the observed statement as OBS, and we model it as a particular if-then else where the second clause is fail. So if the computations do not satisfy this condition phi, the execution is blocked. Okay. As I anticipated, we model the operational semantics as a Markov kernel, which is a function from omega times big F to positive reals. Omega here is the state space, and F is the Borel sigma field of omega. A state, in our case, is a couple, a pair, of store and program, where store is a vector that contains all the values that the variables of the program assumes at a given time. Instead, the program is the program itself, and we model it as a natural number because we assume a bijection between the set of natural numbers and the set of programs. Okay, here, just to give an idea, the Markov kernel plays more or less the same role that the transition matrix plays when considering Markov chain. That is, it tells us how to pass from a state to another, and which is the probability associated with each transition. But Markov chains are defined in a discrete space. Instead, we are considering the most general case in which the state space is a combination of a discrete part, a component, which is given by the program, and a continuous component, which is given by the store, because the values that the variables can assume can evolve continuously, and so it is continuous. So here, just to make an example, we consider the random extraction, and we define the kernel, Markov kernel associated to the random extraction has an integral, so it is obtained integrating with respect to the density G for all the possible value that xi that the variables can take over this section, which is defined here. But this was just to make an example. I don't want to go into the details. I want to stress instead that the observable semantics that we provide in terms of expected value over a function f, which is the function defined over omega infinite, so over the set of paths of infinite length. In particular, here we consider also the probability measure induced by, so mu st, which is the probability measure induced by statement s over path of length t, and the probability measure mu s infinite, which is the probability measure induced by statement s over path of infinite length. Here 0 stands for n times zeros, which are our initial condition, and delta is the Dirac measure, and it encodes the probability measure associated to the initial state. Okay, then our observable semantic is defined as the expected value of function f with respect to the probability measure associated with path of infinite length. We also normalized considering the number of non-fail paths, and this is important because it allows us to update our observable semantics as more information becomes available. And this is important because it allows us to make inference. And okay, this is defined using the Ionesco-Tulce theorem, but unfortunately here we have this measure here, probability measure, which is defined of an infinite probability space, and as it is not directly computable, and as we provide we give an finite approximation theorem that provides a lower and an upper bound of exact observational semantics using only quantities that are defined using finite execution path. So for instance, STFT is the expected value with respect to the probability measure associated to path of length c of ft, which is a function that can be seen as an approximation of function f over path of length c. Okay, we consider going back to our unbounded loops, here, this one. We define f over the set of infinite paths as the value of variable p that takes in the first terminated state of the infinite sequence of states that describe our infinite path. Instead, ft is defined over path of length t, and it is defined as the value that p takes in the first terminated state of the finite sequences of t states that describe our path, if it exists. Otherwise, it returns 0. So we apply our theorem and we obtain these bounds. In particular, all the expected values that are involved in the bounds of our so this one of the finite approximation theorem are estimated using arithmetic means. In particular, they are estimated making applying a Monte Carlo algorithm. In fact, we know that expected value by the law of large number can be approximating using these arithmetic means, where z1, zn are IID random variables distributing according mu_st. Okay, here one could draw values from zi sequentially, so from z1, z2, z2, and so on, and obtaining a matrix which has that has n times t minus 1 elements. Because sampling the single zi means so drawing a value from the single zi means sampling t minus 1 times for our kernel k. And thus, but we have big N zi, and so we obtain a matrix that is big N times t minus that has big N times t minus 1 elements. So rather than proceed sequentially, we decided to proceed vectorially and to sample at once all the independent store, so this vector here, omega 1 n, and so we apply at once all the Markov kernel on all this vector. This allows us to make just t minus 1 vectorized samples from kn, rather than n times t minus 1 samplings from k. And this is crucial because it allows us to exploit single instruction multiple data parallelism, and so this leads to a great speed up in terms of computational times. Okay. So then we have proposed a proof of concept implementation of this framework that we call tensorized samplings and inference, TSI, and that uses TensorFlow, and it allows us to exploit single instruction multiple data parallelism. In fact, we consider, given initial statement, we consider n independent instances of it, and we proceed in a vectorized fashion. And then we apply successive transition of our kernel K in a vectorized fashion, and we use all the samples that we have obtained for Monte Carlo estimation, so to compute the bounds of our exact observable semantics. Okay, we also provide formal guarantees of correctness in terms of confidence intervals using the Efting inequality. Okay. Okay, then we have considered 4 programs, which are 4 loop-free probabilistic programs taken from the literature that are TrueScale, Bagararan, Montiol, and ClickGraph. And we have reported here in these plots the execution times as the number of samples increases. So at the same time, we have also reported the results obtained with WebPPL and R2, which are other tools considered such as the state of the art, and we can see that TSI, which corresponds here to the continuous line, is the fastest in all the cases. So it works very well in terms of computational times. We have seen that it works well also in terms of accuracy. In fact, for instance, considering our unbounded loop that I mentioned before, for instance, it cannot be handled from TSI and WebPPL because it could not terminate. But we apply from WebPPL and R2. We apply TSI and we have computed our bounds for the exact observational semantics, and that I have reported here in this table, together with the probability of termination on path of length T, with the T that goes from 12 to 2002, and the corresponding runtime, the execution time. So we can see that the bounds are very tight, and the execution time is very low, so it works well. We have considered here a number of samples of 1 million of elements. Okay, just the last slide, which is the conclusion, and in conclusion we can say that we have described a probabilistic language together with an operation defined in terms of an operational semantics that directly leads to an exact samples algorithm that can be SIMD parallelized. We have also given an observational semantics and that cannot be directly computed, and so we have provided an approximation theorem to give a lower and upper bound of it. We have developed a TSI, so a prototype implementation that has shown encouraging results. For future work, we would like to extend this work considering sequential Monte Carlo algorithm, because we would like to exploit also all the samples that have been rejected. So, in other words, all the computation that have been blocked by an observed statement, in order to further improve the inference algorithm. So, here are some references, and thank you all for your attention. Thank you.
We have time for one short question, please.
Thanks for the talk. Does this only work if you have Bernoulli distributions, or is it also possible to use other distributions somehow?
All the distribution, both continuous and discrete distribution.
Okay, but I just mean because you use the theorem of large numbers, and I think at least convergence speed wise it's highly dependent on.
The thing is that it is important is that the samples at the end are independent, because otherwise we cannot apply this formula here, Efting bounds inequality, because it only holds for independent variables. And so this is important. So
thank you.
No. Thank you.
Okay, one very short question.
Thanks for the talk. Do you support putting observations into unbounded loops?
Yes, of course.
So, okay, I have a follow-up on that, but we can do that offline. So there are some weird phenomena that happens if that where the expected value is undefined because of divergence if you put observations in loops. So I would be interested what you actually provide as a result then.
Okay, In considering unbounded loops, we reduce them to finite computation, so using this theorem here, and so we consider at the end only finite computation in order to give a bound to the exact semantics that is defined on the infinite computation given, represented by this measure here. This probabilities measure, mu s infinite, is defined over infinite computation path. And it can be used to model also infinite bounds. But when we provide the bounds, okay, for the exact observational semantics, we only consider finite path. So, okay.
Let's thank the speaker.
Thank you.
So the title of the next talk is local reasoning about behavior of classical quantum programs.
Okay.
And the talk will be given by Yuxin Deng. And you will tell who are the this is joint work with
my colleagues Huilin Wu and Lu Xu. So we are from East China Normal University.
Please go ahead.
Thanks. So hello everyone. I'm going to talk about this kind of work about the program logics about quantum classic programs. So here is the outline. So we're going to introduce we call it hybrid classical quantum imperative programming language, and it's very naive language, but we'll give the formal semantics like operational denotation and also axiomatic semantics. And by axiomatic semantics we mean Hall logic. And then we do some case studies about reason about the correctness of some quantum algorithms. Here we are using this kind of architecture for quantum computation. Basically, we are dealing with a kind of classic input and output, but at a certain moment, if we have certain tasks, this should be delegated to a quantum machine to do to run the program, and then give it to a quantum machine, and then it will do some operations. After it has finished this, and we'll get we'll do some measurement to get the classic input. Okay, get some classic outcomes, and then we continue the operation. Okay. And then for quantum languages, actually there still many already some languages. I mean, there's a book about the formal semantics of quantum programming languages, but this is for pure quantum language. Basically, there's no classic construct. You only have quantum operations. But nowadays, a lot of programming languages like Qiskit, Q-sharp, these kind of languages, they are hybrid. That means that we have both classic and quantum operations. And then most of them, they follow the slogan of Peter Selinger. He says that we use, say, quantum data but classical control. That means, for example, if we have conditional or while loops, and the control is a kind of classic. And then the data, we manipulate this kind of quantum data. And for this kind of semantics, or this kind of languages, the formal semantics, we think that it's not well studied. So that's why we are doing this kind of work. And here we introduce a very simple language called QIMP. So we know IMP from the textbook of Glenn Winsker. So he has a IMP, a very simple imperative language. And then we extend it with some with some quantum operations. So let's see, we have some, say, arithmetic expressions like numbers, variables, and some addition, subtraction, this kind of stuff. And we have Boolean operations, so constants like and the comparison of arithmetic expressions or negation, conjunction, etc. And then we have commands. So this line we have these classic commands. So skip for assignment, sequential composition, conditional, and while loops. And this is the last line is what we added for this language. So we have this say initialization of a quantum qubit. So it's initialized to be a catch 0. And then we have the unitary operation. So we apply maybe a gate, say, to a certain qubits, say Q bar. And then this one is a measurement. So we measure certain qubits, and then we get some classical outcomes. We'll do some assignment to this X. Okay, this is basically a very simple language. And to define the operational semantics, we're going to introduce something called a configuration. So we have a command, say a C is a command, and then you have sigma is a classic state, and rho is a density, basically is partial density operator to represent the status of the quantum register. For example, take the very simple statement, say skip. Skip means that you have a start from, say, a classic quantum state, and then it does nothing, basically get to nil, and then you don't change anything. But if you have so this is a classic assignment, so it only affects the classic state. So we don't change the quantum part. And then for the while loop, well, we do the unfolding of this while loop. For this is initialization, basically. We don't change the classic part state, and then we only change the quantum register, okay? Basically, this is initialization on the qubit R. So this partial density operator on rho will go from rho to rho prime. And then we have some measurement. Measurement means that from here, we may have some non-deterministic transitions, go to, say, several branches. Say we go to one branch, which get to nil, and then the classic state, because we may get outcome I, and then we assign to this variable x, so we update this classic state. And then for the quantum part, so quantum state rho will go to see mi rho mi DAC, because we do some kind of a transformation on a super operation applied to this quantum register rho. And then unit operation is this one. So it's very simple. And then in order to define the denotation semantics, we introduce a notion of, we call it partial density operator value distribution. So how to understand this? Basically, it's kind of distribution. Instead of the normal, say, probability distribution, so we assign some classical states with the value is called the partial density operator. So it's defined. So the type is like this one. So here, big sigma represents the set of all the classical states. And then for each classical state, I assign it a partial density operator. Basically, for each sigma, we give it a rho. And then if you sum up for the traces for each sigma, the rho sigma, the trace should not exceed 1. And then we will consider a program or a command as a transformer from a partial density operator value distribution that's called a POVD to another POVD. For example, here, for this kind of classic statement, I start from a pair, so this is classic and partial, classic and quantum state. Basically, we only update the classic part. We don't change the quantum part. Sequential composition, that's easy, right? So first we do the C0 and then the C1. While this is the Euro approximation of it, the interesting one, for example, this one measurement. So we start from this pair. Then basically we're going to get a distribution. It's called a POVD because what do we get? We get to this one. This one means that for all the possible states, say sigma prime, what's the value we're going to assign it? Basically, you consider all the possible sigma from the original support of this mu. So we do the update. After updated state, if this is sigma prime, and what's the value for it? We sum up all the possible mi rho mi DAC. And then if we start from a mu, it's a distribution, we're going to get another distribution. Okay, that's the idea. Let's take an example, a very simple example. Here I have a very simple program. So I do an initialization of a qubit, Q0, and then apply a Hadamard gate. And then for Q1, I do the similar things. And then I measure Q0 and Q1. I get a classical value, say V0 and V1. Then I add up these two values to get V. Okay, this kind of Hadamard operation, so we take this one into a superposition state, K0, K1, and then what we're going to get? So intuitively, we're going to get a 4 possible cases for the classic state. So for here, so for V0, V1, we may have 4 cases: 0, 0, 0, 1, 0, and 1, 1. And then since we take the sum, so we're going to get, say, 0, 1, 1, 2 for them, and then each will have the equal probability, right? And then for the quantum part, we're going to get different values for the quantum register. So basically here is a kind of distribution, right? Because we have a distribution, we go from a classic state to a quantum partial density operator. And then we're going to introduce what's our whole logic for this one. for this program, basically what we want is to have this kind of property. Say we start from, say, anything can be satisfied, any predicate. And then what we want to have is this one. This is the property we want. Basically, it says that we're going to get a kind of distribution state. This one says with probability 1/2, we're going to get v equal to 1. With another half, we're going to say v is different from 1. So this is a kind of distribution formula. Okay, and also for some more say typical quantum algorithms like HHL or short size algorithms, we're going to have more say interesting properties. For HHL, for example, we start from say any state to the end of the program, and we want to have this say on some quantum registers. We're going to get this variable x. Basically, this is the state. Basically, it represents the solution of a linear equations. And for the short algorithm, so we start from a CMP means a composite number n. What we want to get, we're going to get a y. Y is a factor of n, but it's a non-trivial factor because it's not equal to 1 or equal to n. It's a proper factor for it. And then we're going to formally define what's the assertion, because we want to define what kind of formulas are allowed, or predicates are allowed for this kind of hot trippers. And we're going to use classical expressions, classical formulas. So we have different sort of things. So classical formulas, and then we also have say, quantum or state formulas. So classical expression basically is what we see in a, say, first order logic, so the classical things. There's no quantum stuff there, but for the quantum expression, we're going to have, say, this one somehow represent that for the quantum raised to q bar is in this state. And this is a tensor product of two stuff. And the state formula means that either it's a classic predicate, or it's a, say, quantum expression, or something like this O dot represents, this is the idea of separation logic. So we're going to somehow, we split a quantum register into two parts, and they are disjoint. And each will satisfy, say, a different predicates. And conjunction negation, that's trivial. And then on top of that, we define, so on top of these state formulas, we define distribution formulas. So we have this kind of formula represents a kind of distribution. So we're going to say a certain distribution somehow can be split into different branches. Each will satisfy this Fi with certain, say, probability Pi. And on this part, so we don't specify exactly what's the probabilities. Somehow we have kind of non-deterministic choices there. And then here is a satisfaction relation. So, if P is a classic predicate, this is easy because it means that the denotation of this one is true. So this is satisfied. And here for this quantum, this is a state formula. This is satisfied somehow intuitively. It means that if I restrict myself, so rho is a quantum register, right? If I restrict this to this Q bar, and then I normalize the state of this, will satisfy this state. Okay, and then in conjunction, this one means that somehow this is clear, right? Because this is satisfied, so this one satisfies this formula. You see that if I restrict this rho into the free quantum variables of F1, and another one is a restriction to that one, these two things, they should be disjoint. So the restricted state, they satisfy this F1 and F2 separately. Another one, for this one, for example, here, this is a distribution formula. Here, we require that if this is a distribution, we require that everything in the support of this one. So sigma is in the support mu, and sigma and mu rho, mu sigma, they will satisfy this F. For each branch, we should have this. And this is basically is essentially what I said, is distribution formula. So mu satisfies this formula if I can split this mu into, say, the weighted sum of some mu I, and each mu I will satisfy this Fi. Okay, and here we specify this probability Pi, but here for this one, I only require that there exists some probabilities, the Pi from Pi to Pm, so they have this kind of distribution formula satisfied by this mu, but I don't require what is exactly what's the probabilities. It looks simple, and here we define some kind of inference rules. For example, for the classical statements, let's take, for example, this Y rule. This is the non-trivial one. here, so this rule says that we have this whole triple host. Basically means that we're going to have some kind of invariant D. D is a formula. Basically, it's a distribution formula somehow. And it's composed of two parts. So F0 and B, or F1 and then the negation of B. And then here, I connect these two things with a kind of somehow non-deterministic choice, because I don't specify what's the probability is there. And then, so if B holds and F0 holds, and then I do the command C, I will end up with a state which satisfies this D. And then for this part, okay, after the execution of the while loop, so I have F1 and the negation of B. Okay. This one, the following one is a frame rule. So that means if I have F1, C, F2, and this command C does not modify any variables in F3, I will put this as an environment. Okay. Okay, here are the some inference rules for the quantum statement. For example, take this one. This one says that if I have a operation, this is a unitary operation, right? And then I'll start with a certain quantum state. I do this. After that, basically, I only change the quantum registers. Because I'll apply this UQ to this kit V. And for the measurement, this is a little bit complicated because here says that have this whole triple. So I start from, okay, this one says that initially I have a quantum state on Q and Q prime. And then I only measure something on this Q part. And initially I have some PI, and then, well, maybe look at this part first. What we get eventually is a distribution. And each branch will have probability PI. And for each branch, we have this. So this is this one represents the, the state after the measurement, because MIQ applied to V. And this is a classic predicate, PI. And from here, we will get this PI updated by X updated by I. So this is a mimic the classic assignment. But this part is really a quantum rate measurement there. And we also have some inference rules for this kind of iterminable reasoning. And we can prove all these rules their sound. So I will not go into the details. These are very useful when we do some formal reasoning on some programs. For example, maybe you just take one. This one says, okay, basically, I can merge two branches of a probability choice. Basically, here I add up this P0, P1 because they go to the same state. F1. Yeah, we have a soundness theorem to say that if we have a whole triple which is provable in the proof system that we have given before, then this one, the whole triple should be valid. If this is provable, then it's valid. So this is kind of soundness theorem, right? Yeah, we start from here, and then we get to after execution of P, after execution of the command C. So we start from the state mu, it satisfies P. So after execution, we satisfy this P prime. Here I just, well, here is really the proof sketch for the proof outline for the simple program I given before. So we have this the assignment for two quantum variables, and then they apply the Hadamard gate, and then do some sum. And so just using one slice of reasoning, we can prove that or start from, say, true. And what we're going to get is, say, a kind of distribution formula. So V equal to 1 or V does not equal to 1. They will happen with exactly, so 1/2 chance. We also have proved the other algorithm. For example, the HHL, we have a proof sketch like this. For the program here, the non-trivial things happens because we have a while loop. For the loop body, we need to find an invariant there. Basically, here we use this kind of stuff here. Here for the invariant, we use a kind of a distribution formula here. Yeah, here is a proof for the loop body of the HHL algorithm. This is a bit long, so we take 2 pages, but still it's fun. And also, we have other algorithms, say Shor's algorithms. I will not show that. It's a bit longer. So just to conclude what we have introduced, so we have introduced a kind of distribution formulas to represent state of a quantum classical state. Okay. And to describe the behavior, or probabilistic behavior of classic quantum programs. So it's kind of a new quantum Hall logic. And then prove the soundness of this logic. That allows for local reasoning because we have some frame rule there. And the effectiveness of this logic has been demonstrated by the correctness proof of some typical quantum algorithms like HHL or Shor's algorithms. Okay, thank you for your attention.
Thank you very much.
Yeah.
Microphone for questions.
Excuse me?
Can we use that microphone for questions?
Yeah, so.
Hi, so you mentioned there were previously like methods to work with just quantum languages, and now you're working with both quantum and classical. So languages like Qiskit compile quantum plus classical and produce quantum assembly. So why is it not enough to just verify that quantum assembly? Because the classical parts only play a role towards creating this quantum assembly.
Well, theoretically, you can just work with assembly languages. That's fine. But if you reason about quantum algorithms, say I think maybe it's less tedious to write this algorithm in a high-level language, like say maybe it's Q#, or even this kind of language, high-order language, right? Instead of otherwise, because for the while, if you use the assembly language, somehow you need to unroll the while loops. So that's very tedious. If you reason about that, that's okay. I mean, it's okay. But it's simpler to work with a high-level language.
I mean, as it is an automated reasoning, so doesn't matter how much?
No, this is not automated. It's for the moment, we have designed this logic, and we do this reasoning manually. And currently, we have a student. We're going to formalize this in Cork. We try to do a kind of, say, interactive theorem proving, but it's not automatic.
Okay, also, I had one other question. Have you considered like languages like Silk that produce a lot of different other components like uncompute?
Uncomputed, no.
Oh, okay.
No.
Okay, so let's thank the speaker once more.
Okay, thank you.
Keep the mic for questions, or do you want it?
No, I don't need it. So, the next talk has the title Taking Reachability Analysis of BNN Control Systems via Abstraction-Based Training. And the talk will be given by Lin Zhang. And
Yeah.
I'll let you introduce your co-authors.
Yeah, okay, so good afternoon, everyone. You? So my name is Min Zhang. I'm from East China University. So my talk is about how to tame reachability analysis of deep neural network control systems via abstract-based training. So this is joint work with my student and also my collaborators from Oxford University and also Guy Katz from the University of Hebrew University of Jerusalem. So as we all know now, so deep learning is almost everywhere, and so we can use deep learning to train a lot of classification tasks. So besides that, so we also can train like deep neural networks that used to control our vehicles and also devices, various of vehicles, and so most of them, so they are gradually applied to safety critical applications, and so the safety issue of such kind of systems, so they gain a lot of attentions. So there are safety issues. So in 2022, Sesha so published a paper at the Commission of ACM to comprehensively to discuss the safety issues of such kind of systems. So let me just briefly give a very simple example about deep neural network control systems. So imagine that This is a multi-car problem, and it's very widely used in deep reinforcement learning community to evaluate how the training approach to train some good performance controllers. So yeah, this example is very simple. So it seems that we, for this system, we only have for each state, so it consists of two pieces of information. One is position and the other is speed. So using deep learning, so we can assume that we train the deep neural network that can make decisions on each state. That is, so giving a concrete state and the controller, that is the deep neural network, so it outputs an action that is enforced to the device, to the car, and the car will take that action and to move forward or back. So the behavior of the car is determined by what we call the system dynamics, so which is usually differentiable and also nonlinear. So we can compute, actually, we can compute the successor state of the system of the car based on the action and also the system dynamics. So the problem is, so given a set of initial states, we want to know, or we want to compute all possible reachable states in order to formally verify if the system keeps in the same zone, or if it has some interaction with some unsafe zone, so we can guarantee that, we know that so there are maybe some unsafe behaviors that causes accident of the device. So the problem is, so we want to compute, giving a system, such kind of system, we want to compute all reachable state. So yeah, that's a very tough task actually. So let's first imagine that how we can compute giving can create an initial state. So how could we compute its successor state? So we know the mechanism of the controller is, so it takes that state and feed that state into a deep neural network and to compute action. And then based on that action, so and also system dynamics, we can compute its the successor like this from S0 to S1. And the relation, the computation is based on this equation. So this is the current state, and so for each time horizon, we assume that the action so it's constant. So we can use system dynamics to compute the successor state. But the problem is that, so if we are giving a set of state like S0, and we want to know after one time unit, so what's the set of successor state? Because here the successor state is usually infinite and continuous, so we cannot enumerate all the state and compute it. So to do that, we want to compute the successor state like we do on the concrete state. So if we want to do compute the set of all the successor states for a set of current state, so we need to know so what kind of actions for each state in SI, because here the deep neural network, so it's almost inexplainable. So we cannot enumerate. We cannot enumerate all the states here. So the traditional way to do this is to overcome, to do some over-optimization, linear over-optimization to approximate the deep neural network and try to use some like Taylor models instead of deep neural network to compute the successor state. But we observe that such kind of approach will introduce a lot of overestimation because of the over-approximation of the deep neural network. So in order to reduce such kind of overestimation, and our solution is that if we can partition the set of state into a finite set of subset, and if we can guarantee that for each subset like this here, there is one, so the deep neural network, the controller make a unique action on each set. Then we can reduce this equation. We can get rid of the deep neural network to compute the success state. That is, we can reduce this problem into the reachability problem of a hybrid system, because we can get rid of the deep neural network controller. And there are several tools that can be used to compute the reachable set for hybrid systems. So our starting point is, so we want to make sure that for each subset in this partition set, so we need to guarantee there is unique action. But that is almost impossible for traditional training, because so the neural network, so it takes each concrete state as input, so it doesn't guarantee that property. So our solution is that instead of train the network and then partition the subset, partition the set into subsets, so we try to first divide the state space into several pieces, and then consider each piece as a whole. That is the initial the state in each partition set, so they are distinguishable to the controller. So that's our solution. So this is the traditional approach, and in our approach, we first divide or partition the whole state space into several pieces of the state, and feed each partition set into the neural network. This is a specialized neural network that can accept the set of the state instead of a concrete state. So yeah, that's our solution. Yeah, you can see the difference between the conventional training approach and also the abstraction-based training. So in conventional training approach, so we feed each concrete state into the network. But in our approach, we feed each concrete state into a network. But in this specialized network, so we have some special layer we call the abstraction layer. So this layer, so the purpose of this layer is to transform each concrete state or map this concrete state into its corresponding partition subset. So in this way, we can guarantee that all the states in a partition site, so they will uniquely mapped to its corresponding partition and make the unique action. Yeah, so that's the that's the way how we can encode this abstraction layer. Like for each set, for this set, so we encode the abstraction layer like this. So it can be straightforwardly encoded like a part of network, and so notice that we don't need to train this part. We don't need to train this layer, and we before training we just fix all the possible corresponding like activation functions and the weight, and to do the transformation. And so once we train the network, so computing the reachable state becomes easier. Like giving a set of states here, assume that currently we want to compute the successor state for all the states in this part. And our way is to first partition this site into different pieces according to the actions the network makes. And then for each one, because for each subset, it has a unique action, so we can compute its successors and then combine them together. So yeah, that's the basic workflow of computing the reachable state like this. And we did some experiment, and we found that so in our approach we can compute more tight and more tight reachable state, like compared with some state-of-the-art tools. Yeah. And also, yeah, we completely evaluate our approaches on the benchmarks in this field, and we observe that for other white box, we call it white box, like VMCAI or Polar, they are white box tools. So in some cases, we observe that they have to terminate because they introduce too much of estimation, or they terminate because of timeout. But our approach can succeed in most of the cases. And we also want to know if such kind of special training cause some time overhead. Yeah, it's for the abstraction-based training, so it takes a little bit more time to train in order to get the similar performance. That is because we have a special layer, and it causes some additional computation. But the point is, we can train the specialized network and to make it have almost the same performance as the Euro networks. So here is the experiment about the under some kind of perturbations. We want to see how the controllers perform. And we also observe that some kind of abstraction may cause the explosion of partition, because for each partition we need to guarantee so it has a unique action. And this may downgrade the performance. So in order to have the similar performance, we need the fine-grained partitions that may cause the partition explosion. And our solution is that we do not assume a unique action. So we assume for each partitioned set, so we assume there exists some linear controller. So the linear controller is more expressive than the constant. So in that way, so we can get rid of partition explosion. So this solution is published on the NIPS, so 23. And yeah, so that's basically all what I want to present in this talk. So basically, we introduce an abstraction-based approach for in order to train verification-friendly controllers. And actually, this is the follow-up work based on our SIGA-based training and verification published at CAVE last year. And so there are several field work to do, like beside of interval-based abstraction, we want to introduce some more sophisticated abstractions and to train the network. And we also want to know if it's possible, like, to introduce such kind of reachability analysis for runtime verification. Yeah, that's all for my talks. Thank you. Here are some references.
So maybe I have a question then. Yeah. This partition, so you use the intervals for the partition?
Yes, now we use intervals.
And do you take intervals of a fixed unit length, or how do you choose the length of the intervals?
Yeah, that's a good point. So actually in our previous work here, we first introduced some coarse-grained partition interval. But we may fail to verify some properties because the decision is too coarse. And so based on the verification result, we refine the interval gradually. Mm-hmm. And then we can achieve equivalent performance as well as so make sure some properties are verified. Yeah.
And
It's
so,
yeah.
and so after the refinement, you guarantee that each box has a unique transition relation?
Yeah, that's the actually the property we need to guarantee like that. And as I said, so it may cause the partition explosion because so actually we cannot do the same action like for some partition. In that case, we need to partition it into 2 pieces. Yeah, and it may cause, if we have high dimension, so it causes the explosion.
It may cause non-termination also. Right?
Yeah. So our solution is that we are trying to extending this assumption to be nonlinear, not a constant. Yeah. In that way, so we can approximate the controller as the one we trained on the concrete state. Yeah.
Okay. So if there are no more questions, then that's great. Thank you very much.
Thank you.
Okay, so the last talk of this session. Okay, the next talk of this session, not the last one. The title is Verification of Neural Networks, Local, Virtual, Classification, Private.
All the words are only connected in this fork. They have no connection outside of this fork.
Buzzworthy.
I mean, neural network tends to connect together outside, but that's it basically.
It will work. We tested it before. We shouldn't have done that.
I tested it before. It's connected.
Yeah, I know.
Your computers see the screen. Oh, maybe I'm just.
Is not connected. Try to plug and unplug. Use an adapter, maybe. We have an adapter, maybe we can try.
Can we try yours?
Wait to the Type-C, I don't know.
It's not Type-C, it's HDMI.
No, yeah, we try to use a Type-C.
Is Type-C?
Type-C? Oh.
We try to use another port, maybe it's working. Type-C. Maybe in this way.
Alright, the sound of something connected.
Yeah, that's it. I don't know if it's your fault or the system fault. I think this is okay. Now it's working. I don't know why, but right.
Yeah, it was strange.
Alright.
Please go
So,
ahead.
hope everyone hears me. So I'm Levi Chef from the Technion in Haifa, Israel, and I'm about to talk about my paper, verification of neural networks, local differential classification privacy. As I said before, if you understand each word separately, this is enough for the start. The words are only connected in this paper. So let's get. So first of all, neural networks. So we know neural networks, they're very strong, but they're also vulnerable to privacy attacks because we use training set to train them. The training set contains sensitive information. And the privacy attacks can use this sensitive information that exists in the training network to extract or infer the sensitive information. Even in black box settings, and for example, the membership inference attack can infer whether a sample is a member of the training set or not a member of the training set. And it can be very problematic in many settings, privacy problematic. So when we talk about privacy, the most popular and common is called a way to quantify and inject privacy is called differential privacy. And what does differential privacy mean? It means an algorithm is differentially private. In our case, a network training algorithm would say it's differentially private if the result of the algorithm, aka the trained network, is or has a similar probability distribution, whether it was trained on the full training set or whether it was trained on a training set that is different in one sample, a differential training set, if you will. So the full training set or training sets that miss one sample should look roughly the same, make sense, right? One sample shouldn't really matter. So if it really doesn't matter, we say it's private or differentially private. And any algorithm can turn into a differentially private if we simply add noise after we did the private, use the private information. For example, in network training, we usually add noise after every gradient step. And this is all really great, but when we add noise, we decrease the performance of the network, which is undesirable. And also, we have to initially train the network to be differentially private for it to be differentially private. A network that was trained normally will never be differentially private because only randomized algorithm can be differentially private. So we would like, given a network that was already trained by a general training algorithm, we would like to quantify the privacy or give privacy guarantees on this network that was already trained without changing the training process. So since we cannot use differential privacy, we have to invent a new privacy criterion, which we call local differential classification privacy. And the idea is that to use the idea of differential privacy by looking at a training set that are differential in one sample, however, in a deterministic setting. And we basically extend a local robustness property in this differential setting, and this is how it looks. So local, we look at a specific neighborhood, and differential, we look at the training set compared to the training set that is missing one sample. Classification, we only look at the classification of the part, and this is the privacy. So we look at the network that was trained on the full training set and that was trained on a on differential training set for any sample that can miss. And then if all of them are locally robust, we say that it is private, or LDCP in our case. Right? And if it's not very clear, then basically this, by this definition, there is a very naive algorithm in which we can make sure whether a network is LDCP or not, and just by following the various steps. So for every entry in the dataset, we remove it and train the network without this sample. And then we check local robustness on our neighborhood. And if it's local, and if everyone, all dataset size plus 1 networks are locally robust, then we say, oh, LDCP. And else, no. And this is really great. It gives us the optimal result. If only not, we needed to train D+1 networks and verify D+1 times local robustness. So this naive algorithm, while it gets us the results we want, is not practical. So we would like to do it without training that many networks. So our idea is called Sphinx, Safety Privacy Analyzer via Hyper Networks. And it works in 2 steps. And the step and connecting them is a new object we call a hypernetwork, which is basically an abstraction of all the possible D+1 networks. And instead of training the D+1 networks, we predict a hypernetwork. And then, instead of verifying local robustness D+1 times, we verify LDCP once on the hypernetwork. And now we'll talk about each part. But before that, we'll talk about the hypernetwork itself. So in order for our idea to work, we need to define what is a hypernetwork. What is this middle object? So the hypernetwork is an abstraction of the networks. So the way it works is that it looks like a regular network, but each network parameter or a weight, instead of a number, is an abstract element. And we chose the intervals because intervals are very simple, which helps us, but they're also not very super simple. Like we can tell some things about them. And if we have all the networks, then getting the hypernetwork is very easy. We take the minimum and maximum number for each weight. But we cannot do this because we don't want to train all D+1 networks. So we have to predict the hypernetwork from a small number of networks and cannot use everyone. So how do we do it? So we train a small number of networks, each one without a single unique sample. We predict a hypernetwork by predicting an interval for each parameter independently, which we can do because intervals are non-relational abstractions. And then we check whether our hypernetwork is good enough by comparing it to the hypernetwork from the previous iteration. And if they're similar, then we say the algorithm converged and we're okay. And else, we go and train more networks. So we'll be also adaptive about the number of networks we use depending on the difficulty of the problem. So now we'll talk about how we predict an interval. So when predicting an interval, we reduced our problem from predicting a hypernetwork to basically having a few samples from an IID distribution. And we don't know what the distribution is, but we know we have samples from IID distribution, and we want an interval that covers all the samples from the same distribution that we don't see. If we knew what the distribution was, it will be very easy. But we don't know. And we cannot assume we know. We cannot assume, for example, we cannot assume it's Gaussian, because it will just be a lie. Right? It's real data we train. So the idea is that we'll transform the values into a distribution we know. And the distribution we know will be using a kernel density estimation, which is good for estimating. But we not just use kernel density estimation to estimate the distribution, we'll also transform the data into something it will be easier to estimate. And it works like this. So first, we normalize the data, which is very important because it centers it around 0 and make everyone the same scale. And then we transform the data into the distribution. And then we compute a confidence interval. And eventually, we undo the transformation normalization on the interval to get an interval for the original scale. And this is a well, won't go into the specifics of this, so we'll just have the one. All right, so this was the prediction part, and now the verification part. So the verification of hypernetwork is very similar to the verification of local robustness of a normal network. We exchange a normal local robustness verifier, specifically the mixed integer linear programming verifier, which we use because it is a complete verifier, and it doesn't induce any over-approximation, which is very important because the existence of the hypernetwork already induces over-approximation to our problem. So we don't want to induce more over-approximation, make it unsolvable. So we have to use the strong verifier. However, using a naive extension, we lead to quadratic constraint because the linear layers, we have a weight times neuron. And this time, both the weights and the neurons are parameters. So we cannot do a naive extension. However, if the layers input are non-negative, then we can bound it using the upper bounds of the weights and biases and the lower bound of the weights and biases, because the input is non-negative. And now, instead of each linear layer, instead of having one equality constraint, we replace it with two inequality constraints, which is the same complexity. And the activation layers don't have any parameters, so their encoding remain unchanged. So this is the only difference. One equality constraint turned into two inequality constraints. All right, now about to evaluate. So we implemented the code online, and we use a 3 data-sensitive dataset, adult census, bank marketing, and default of credit card clients, nicknamed adult, bank, and credit. Here you can see the D+1 of each one, big numbers. And each of them was trained on, they're all binary data sets. They have binary output. And we use, each of them was trained on 3 types of binary networks, of fully connected binary networks, 2 hidden layers of 50 neurons, 2 hidden layers of 100 neurons, and 4 hidden layers of 50 neurons. Right? And so how effective it is. So in order to talk about LDCP, we need to talk about the local part. We need a neighborhood. Without a neighborhood, we cannot talk about LDCP. So we use 3 types of neighborhoods. The membership neighborhood, which is just the sample itself. DP robustness, which is the standard local robustness neighborhood, infinity norm of size epsilon. And the sensitivity or individual fairness neighborhood, which is all samples that are exactly like our sample, except for one sensitive attribute, such as gender or age. So these are the neighborhoods we worked with. And we had 100 neighborhoods of each type for each data set. And we compared it to the naive algorithm to get true positive, true negative, false positive, and false negative. These are our results. So we can see membership is the easiest neighborhood. So a lot of true positive, not really much getting true negative and false positive, and few false negatives. Very, very easy. We do have over approximation, so we do get few false negative. DP robustness, a bit harder, so we have a few more true negatives. And also in sensitivity, we can see that the false positives that exist because the hypernetwork might have under approximation are very rare. So it's a good thing. Right, and this is the running time. So you can see the number of trained network that the naive algorithm used, which is D+1, and our algorithm used, we see great improvement. The training time is proportional to the number of networks we trained. So you see the same improvement. However, the best improvement is actually in the verification, because instead of verifying D+1 times local robustness, we verify LDCP only once. And we do it once per neighborhood. So if we have a lot of neighborhoods, this is the bottleneck. So this super great improvement is very important. So now, how good we predict an interval? So we look only on the thing we call the weight abstraction rate, which is the percentage of the weights that are fully abstracted by the hypernetwork. That all of them are fully abstracted. And we compare a few variations of our algorithm. So we have the interval abstraction, in which we get a few networks and we get the minimum interval that include all of them. Get bad results. Minus transform, we do not transform the data before we assume we know what the distribution is and estimate it, and it gets moderate result. Minus normalize, we transform the data but without normalizing it first. Horrible results. Normalizing the data before transforming is important. Minus KDE, we do not use kernel density estimation and instead transform the data into a Gaussian distribution as normal, and also get a moderate result since we do use transformation. And predint, our algorithm for predicting an interval, it gets the best result because it uses all of the things together. By predicting a hypernetwork, we compare the interval abstraction to Sphinx. And the network abstraction rate is the percentage of networks that are fully abstracted by the hypernetwork and are fully included in the hypernetwork. And the interval abstraction, it really depends. It really depends on luck, but on our algorithm, we always get more than 90% of the networks that are included. All right, so in conclusion, we have a new privative property, local differential classification privacy. We have a verifier that verify LDCP by training small number of networks, creating a hypernetwork, and verifying LDCP directly on the hypernetwork using normal local robustness verifier bit modified. And this is our results. We trained only 7% of the networks, and our hypernetwork contains more than 90% of the networks. Our verification accuracy is 93%. And the verification times is 17,000 times faster. So, any questions?
Hi, I have two questions. The first is, how is hyper neural networks different from abstract neural networks?
When I saw the abstract neural networks, the abstraction was completely different and for different purpose. When I searched for what is an abstract neural network, usually they combine neurons together. You had one network, and you combine the neurons together to get an abstraction of the single network, so that the verification process will be faster. But here, we have multiple networks, and we use one network to abstract all of them.
So
it's a different thing.
So you're joining new networks instead of joining neurons.
Yeah, but it's a different thing because it has a different purpose and like we don't do it to make verification of a single network faster. Like instead of making a single network smaller, we join many networks that we all care about all of them together. Okay. So it's different. They're not related to each other.
So the second question was like given the threat is the loss of privacy, like have you considered the work in the context of federated learning?
What do you mean about?
Federated learning as in like the Google translator app, the Google keyboard learns how to predict the next word by...
Yeah, I know. Federated learning is when multiple agents work together for the same task.
There is a lot of work for privacy in that case, so could that be more integrated with your condition?
So the thing is, our algorithm need to train the full network from scratch. So for our algorithm, so the one who runs our algorithm need to have access to the private information. And in federated learning, nobody have access to the full private information. And that means that probably either we need to change it or it won't work because you need some sort of a local agent that has all the private information and runs our algorithm. So it works more in the case of a single silo that you just get it all, you have all the data and you take our algorithm and run it on your own computer that the private data will not leak. So I'm not really sure how it will work with federated learning.
Thank you.
A quick question. Yeah, so is it possible to train a hyper network directly?
To what?
To train directly.
Yeah, so I thought about it, but the problem is every epoch, the intervals will increase and increase and increase and increase until they're not relevant, unless you have a really smart idea to use the whole connections, then you can use like something much smarter than the intervals. But the thing is, I still like the intervals because the intervals make it both the prediction and the verification easier. Because even the verification, we swapped one equation with two inequalities because we had intervals and not because of all other things. And also, it's really hard to track all the changes correctly. So yeah, it will be ideal if we could train it directly, but it's really hard because network training is not a simpler algorithm. So we'd rather just look at the results and compare them to each other.
Okay, so let's thank the speaker once more.
Thank you very much.
So we are only 7 minutes late.
Yeah.
So the next talk has the title Agnes. I give the German pronunciation. Abstraction Guided Framework for Deep Neural Networks Security. Please.
Thank you. Yeah, I'm Akshay Danti. I'm a PhD student at University of Twente and also an employee at Audi. And this is done with my colleagues Marcelo Ayman and Dr. Fahid Hashimi from Audi and my supervisor, Dr. Hans Moritz from University of Twente. So today I'm talking about a security technique to identify some security risks in DNN, deep neural networks. I'll quickly give an overview of where this is used. Since I'm working at Audi, our use cases are more towards the perception system for autonomous driving vehicles, and we are looking into these cases where they're risky. I mean, there is high security risk because these are safety critical systems, like, for example, scene understanding or rules of engagement. We cannot develop systems without perception or deep neural networks involved.
And it's important that we make sure that they work all the time perfectly. The problem here is that we train these neural networks with a very large data sets for a very small example with a small image size of 32 by 32 pixels with 3 channels. We already see like 2.4 million parameters to get like a very nice accuracy, and this is huge for verification, any verification or testing techniques to work. What we ideally expect from the network is to get like a given input image. It has to always predict correctly, but then there are some issues here because this cannot be always perfect. There are some reasons, many reasons, but I'm focusing towards security risks that can happen. And these things can be unknown biases that are in the network, which cannot be seen because we train on a large data set, which we don't know what it contains. And there can also be some intentional attacks. For example, the data can be somehow manipulated, and there is no way to tell because you do not have like a direct understanding from input to output of the network. So we have a network which is black box in the middle. There can also be some poor training data because there can be, if you do some statistical analysis, there can be imbalance in data because you always don't get all the data for all kinds of problems and classification, and this is really hard to get balance every time. So these things are called backdoors in the network, and we are trying to focus on identifying these backdoors. One of the real-world scenarios, this is the bus from Ingolstadt, the city where I'm working. So this kind of traffic signs on the bus as an advertisement can lead to wrong predictions. First of all, it's detecting that as a traffic sign, but then it is predicting entirely something different because of some disturbance on the image. And this can lead to some accidents that was not foreseen. And this is the kind of motivation on my work, and the talk is mostly divided into how the technique Agnes works, the tool Agnes works. So I try to go into like 2 steps. I explain the building blocks of the tool, and then about the overall framework, and then we see some results. So the first module is the artificial brain stimulation. This is a technique from 2019. What it does is, given this kind of system, we look into hidden neurons in the network and then stimulate these neurons, try to modify their values to see if it will lead to a misclassification. And the point is to finally get like a set of neurons that are considered compromised, and then we analyze it to get some understanding why this happens. Now the number of hidden neurons can be huge, so that's where my technique comes in. So we try to somehow abstract the set of neurons based on some clustering techniques. Now I'll go into the module 2. This is a clustering method, and we propose 2 different kinds of clustering methods. First one is the approximate based clustering. So you see on the left, this is the neural network, and then what we do is cluster them in each layer to get some groups, and then we identify the cluster representatives, which are the groups are in colored and representatives are highlighted. What we propose is 2 different methods. One is we try to only stimulate the representatives and then find the compromised neurons from the representatives. This is the approximate method. And then the other is we use a technique called deep abstract, which kind of removes all the neurons that are part of the cluster by moving the weights into the representative, and then we use this abstract network to then stimulate and then find some triggers. Finally, I'm talking about triggers here. I just want to quickly show how the triggers are developed. So this is again from the module 1, the IBS, artificial brain stimulation. We do some optimization to find out the triggers based on the compromised neurons. Now, the reason we have these 2 different techniques is because we are dealing with larger networks, and the abstraction or clustering methods do not always work on industrial functions, which are huge and also has complex layers. That's where the tool that we developed comes in. So we have a way of we try to find out the kind of layers that are in the network, and then based on the complexity, we then go into the different methods, and all these we try to find the right method for our approach, and this is done automatically. And we're also dealing with to make this generic, the tool to be generic, so we can handle the networks from different frameworks like TensorFlow and PyTorch, because we convert them into ONNX kind of version model, which is like a generic one, and then analyze this. And then based on the complexity, like for example, if the network has layers that are for beyond CNN, convolution neural networks are fully connected. If they are complex, then we go into the approximate method by flattening them out, finding the cluster representatives, then putting them back together, and these representatives go in different places and then stimulate each channel separately. And then if it's contains only CNN and FC layers, then for the CNN layers, we convert them into fully connected, because the convolution networks are nothing but sparsely connected, fully connected networks, which means you can easily convert them, but this will put large number of neurons in the hidden layers. To reduce them again, anyways, we do the abstraction where most of the non-necessary neurons are removed. And all these modules which in the tool are function agnostic, which means the clustering and stimulation techniques can be replaced with newer approaches. Right now we just took the state-of-the-art methods to do this. For the experimental setup, we looked into several different kinds of triggers. Something new that we tried is put some transparency properties into the trigger. We made it a bit more transparent, so that these triggers which are put in the Trojan network or the attack network are sometimes not seen when you apply this on the real data. And we actually looked into large model architectures and also considered state-of-the-art architectures like VGG, GoogleNet, etc. And then combination of benign models and attacked models, we did around 400 experiments for different kinds of triggers. And as you can see, the primary parameters that the network we consider are very large, from 80,000 to 3 million parameters, which means most of the techniques that are they are currently there right now would not work even for abstraction or for security analysis. And to look at the results, we were able to identify more backdoors. These backdoors are nothing but the triggers that are meaningful based on analysis after we reverse engineer them. And these backdoors were, gave us better idea. Sometimes the techniques like ABS and ENS neural cleanse, which are benchmarks for us, they could not identify some of the backdoors that are there. And with runtime, since we are abstracting the network, we are also able to reduce the runtime of stimulation. Then about the results on different triggers, like I said, since we played around with transparency, with the low transparency, which means the triggers are not seen easily. Since we are clustering and then stimulating, our chances of finding the backdoors were highly likely, and that gave better results. For the approximate simulation, the clustering rate is very important. So this is something we have to find out manually. And this is where there is some room for improvement in the next phase of the project. For abstract method, anyways, the clustering is controlled based on the drop in accuracy, so we don't have issues in the other method. So this is the tool, and thanks for listening.
Thank you very much for the talk.
Thanks.
So we are 8 minutes late.
Does this tool also protect or try to protect against these adversarial examples where it's meant to look to human eyes like a 50 kilometers an hour sign, but it's interpreted as 90 by the car or something like this?
So adversarial examples are a bit different. They do not have triggers usually. They play around with the way the gradients are learned, and we focus on security risks. Adversarial risk, you need to have the access of the network, which is usually not the case. So if there is something manipulated in the data, and then these techniques work. For adversarial work, we are looking into robustness analysis more in a more formal meta-based approaches, but this works on only small networks right now.
Thank you.
Okay, so let's thank the speaker once more.
Thanks.
at 4 for the final session where we tell who got the best paper.
Okay, so let's get started. Welcome to the final and thus closest to POPL time-wise session of VMCAI. We'll have 4 talks and the closing, including the announcement of Best Paper Award. And our first talk is software model checking for programs with dynamic thread management, also called petrification. And the talk will be given by Frank Schüssele.
Yes, thank you for the nice introduction. So our contribution is to develop a practical verification algorithm for programs with dynamic thread management. So to get started, we first need to get to know what exactly is dynamic thread management. So dynamic thread management is motivated by C. There in the pthread library or POSIX thread library is one way to create, to write concurrent programs. There's also a similar concept is also used in other programming languages, for example, like Java and also others I'm not too familiar with. The key features are that there is a fork in the pthread library. It's called pthread create, which can be used to create a new thread dynamically. And there's a join statement in pthread library. It is called pthread join to destroy an existing thread. So these are just usual statements in this programming language, and they depend on the control flow and data flow, because maybe the fork or join, it might occur inside of a loop or inside of an if, and thus it may depend on the evaluation of some program variables or some expression. And now let's take a look at an example for dynamic thread management. We have 2 thread templates here. One is the main thread that is initially active, and on the right-hand side there's a worker thread which is blank for now. We will take a closer look to that in a second, but for now just let's take a look at the main thread. So we have some statements there where we initialize variables or some if and some while. And inside the while, you can see there's a fork statement. So it really has the syntax that as the first argument, you have some expression that is the thread ID of this thread. And as the second argument, you have the name of a thread template. So what this means here is inside the while loop, we create a new instance of the worker thread. And as you can see, it happens here inside of a loop. And this loop is just a non-terminating loop, which means we create infinitely many instances of this worker thread, assuming here that there are unbounded integers. And this worker thread is identified by the first argument. So what this means here is that every instance of the thread is identified by the number of iteration it was created on, because the I is here used to count the number of iterations. And also you can see there's a join. It even happens inside of an if, so it really depends on the control flow and data flow, which means here this join is not executed in the very first iteration, only afterwards. And what this does is it destroys an existing thread that matches this thread ID. So here we join the thread with ID I-1. This means that we just destroy the thread that was created the iteration before. So, and this means that although there are infinitely many instances of the thread, at most 2 of them are active at each time, because we create one instance, and the next iteration we create one again, but then we destroy the one from before, and so on and so on. But now let's take a closer look at the worker thread. So here the worker thread is rather simple. It first increments this global variable c by I, then asserts that it still satisfies some bound using an assertion, and afterwards decrements c by I again. And now we ask whether this program is correct. which means does it always satisfy its assertion? And this program is indeed correct, but it's not as obvious because it's really complicated, this thread creation and destruction and so on. So we want to develop a verification algorithm to check this for us. But first, I want to introduce the concept of the thread width. The thread width is simply the number of instances of a thread template at any point in time in any execution. So consider our example again. We have seen that there are infinitely many thread instances at each point of time. However, only a finite number of them are active at the same time. So this means the example just had a thread width 2. Now I want to present our verification algorithm. So first, we start to model the program by with a fixed number of thread copies n. Usually we start with n equals 1, but this can be changed. And we represent the control flow of this program using Petri nets, and thus the name petrification. So then we have such a representation of the program with only a fixed number of thread copies. Then we apply an existing verification algorithm to such a Petri net. And this, depending on the output of this verification result, we may start over again, which means if n is less than the thread width, which means that there are more than n threads active at some point in time, then we increase n and repeat over. So we then model the program with a larger number of thread copies. Now let's reconsider our example again. On the right-hand side, you can see the example. On the left-hand side, you can see the petrified version of the program. So the Petri net representing the program with one thread copy. So there are several places here, and some of them are simply used, those without labels, to track, to represent the program locations. And others, like not in use, and insuf, are used to track the active threads. So we also call them thread monitor places. And also on the very top, you can see there's an error location. So therefore, since it is an error location, it is labeled as an accepting place in the Petri net. And also, you can see I split some by colors there. So on the very top, there's a thread copy of the worker thread. On the bottom, there's the main thread in red. And yes, and you can see that there are tokens in the places. So initially, only the main thread is active, so it has a token in its initial location. And the worker thread is not active, so there's a token in its not in use place, so it is not used yet. It was not forked yet. And yes, there are obviously also transitions connecting the places, so many of these transitions are simply used to represent the control flow inside the threads. For example, the transition on the very left simply initialize the variables and shift the token one to the next location of the main thread. However, there are also some, okay, the same also applies for the other control flow features like loops and if. But then the question is, how do we model the fork and join in this Petri net? You can see the fork is, so one instance of the fork is modeled here. So we simply say, okay, if we are in the given location of the main thread and this thread is not used, then it is used afterwards. And to track that we have the correct instance, we also introduce some thread ID variable and assign the I here that we can see from the join for the fork. We assign this I to the ID variable. And this the join also makes use of this ID variable, and it simply checks, is this the correct thread to be joined? And then it terminates the thread. So it was used in use before, this no more used afterwards. And there's, however, a second transition derived from the fork. This is this here, labeled with true, so we can always take it. What it says is, okay, we have only one thread copy, and if this thread copy is already in use, and we try to fork another thread copy, okay, then we know our modeling was not sufficient, because there is only one thread copy, and we want to create two thread instances. Therefore, we label this also as an error location, as an accepting location. Now, let's show a run in this Petri net. So, okay, so first we execute the very first statement, an initialization of global variables in the main thread. Thus, we shift the token to the next place and fire the transition. Then we execute the fork, so the fork on the top. Then we shift the token from not in use to in use, add an additional token to the initial location of the worker thread, and also continue in the main thread. Okay, then we do two more transitions in the main thread. So the if condition is not satisfied, so we skip over it and do not a join. Then we increment I and start over with the loop again. However, then we can execute another fork. But our only thread copy is already used. Then we can can fire only this insufficient, this transition to the insufficient place, and thus reach an error place. So this means one thread instance, one thread copy was not sufficient to model program. What we do then is we introduce another thread copy. It looks really similar. Now we have on the very bottom another thread copy for the worker thread. And now we apply our verification algorithm again. I won't go into detail. However, the verification algorithm for Petri nets then concludes that this Petri net program is indeed correct. And thus, the program on the right is also correct. Okay, now let's get to some challenges of this algorithm. So for the fork, we need to ensure that no active copy of the thread template is reused, because there only one copy can be used at the same time. And for the join, we need to ensure that the matching instance of the thread copy is destroyed, and this depends on the evaluation of the thread ID. Okay, now let's take a look at the implementation. This was implemented in the Ultimate tools, Gemcutter, Automizer, and Taipan to verify C programs that use the POSIX thread, so can really model the pthread create and pthread join by fork and join, seen in our example. And these tools are the top 3 tools in the SVCOM 2024 concurrency safety category. Okay, now it's time to conclude my talk. So our contribution was that we have a practical verification algorithm for programs with dynamic thread management. It has proven to be successful in SVComp. And this algorithm has some nice property. It is complete for programs with a finite thread width. So if there are only a finite number of threads active at each point of time, we can actually verify this program. There's, however, some small side note. This only is true if the underlying verification algorithm that verifies our PetriNet program terminates. So that's it. Thank you for your attention, and I'm happy to answer any of your questions.
Time for questions?
Did you consider using colored PetriNets, since you seem to have many copies of the same subnets?
I'm not too familiar with colored PetriNets. Something I did not mention is we have a verification algorithm for PetriNets, but only for one safe PetriNets, which means in every place, at most one token can be.
One safe.
Yes.
Okay. And if I may, a second question.
Sure.
Will you consider adding timing constraints? Would it be useful? For time PetriNets.
I have not thought about that. We use this mainly to model C programs and without any timing. Yes?
Does your tool model data races?
It's not right. We have, okay, let's go back. We have this verification algorithm, and we apply it to a program that looks something like this. It just has, it checks for assertions. So this tool does ignore that. However, what we do is we translate a C program to a program which looks something like that. And in this modeling, we can also model data race and check for data races.
I actually had one question about what you mentioned about the restriction of the underlying PetriNet model checking algorithms.
Yep.
What consequences does this have for the problems that you can check? So does it mean that in certain cases it will not manage to verify, or will it?
So what do you mean the property for this?
One safe. Do you always generate such PetriNets?
Yes, this algorithm always generates such PetriNets.
Any other questions?
So you only check assert statements, so you do not consider liveness properties, just safety properties?
Yes, this is true. There is, however, some kind of ongoing work about that. I mean, the modeling itself could work similar. We need just a different acceptance criterion for this PetriNet program.
Okay, if there are no further questions, let's thank the speaker. Our next talk is a fully verified persistency library, and the talk will be given by Brijesh.
Great. Thank you. So I should speak into the microphone, is that right? Okay. Yeah, so this is joint work with a number of people that you can see on the screen. Heike is also here in the audience, so maybe she'll be able to answer some questions that I'm not able to answer. But this is basically an exercise in verification, I would say, and we're trying to verify a particular library that allows you to transform a concurrent algorithm, a linearizable concurrent algorithm, into one that's called a durable linearizable concurrent algorithm. And the proof is via a number of smaller refinements, very small refinements, and a few sort of techniques to sort of transform the algorithm as well, which I'll talk to you about in a second. Okay, so, right, and persistency, right? So there's this sort of this mysterious word that might be a little bit confusing to some people. So what is persistency exactly? So the sort of architecture we're looking at is a bit like this. So we have multiple threads, concurrent threads, accessing two different types of memory. One is a volatile standard DRAM, but also this sort of non-volatile memory, which became very popular for a long time, well, for a while, because Intel invested a lot of money into this Optane technology, which they then pulled the plug and made a lot of people disappointed. But this is sort of this technology that allows you to sort of treat this non-volatile sort of persistent memory in a byte-addressable way. So it's very efficient compared to sort of standard storage. And yeah, so various technologies, Intel, which is now discontinued, exists, but sort of others are sort of picking up the pieces. For example, CXL and memory semantic SSDs and so forth. So this research is still sort of ongoing, even though Optane has died, is what I'm saying. Essentially, what it allows you to do is sort of develop very high-performance recoverable applications. Okay. So just in case you're not sure what happens with persistent memory, you kind of have two copies, essentially, of your data, and you first start writing to DRAM, and then occasionally that's sort of backed up to NVRAM. And the good thing with the NVRAM copy, even though it might be a little bit stale at times, is that if you ever have a crash, you can recover from it, right? So you can sort of copy back your non-volatile memory into DRAM, and then you've got sort of some kind of recoverability possibilities, which you didn't necessarily have if you just used DRAM. So you basically, you don't have to start from scratch. Okay. Just to give you some idea of what you can do, you can sort of control the way you write to persistent memory. So programmers are expected to control the way you write to persistent memory, because otherwise you will end up with inconsistent algorithms and incorrect algorithms. And you can sort of use sort of various instructions that developers have provided, or hardware developers have provided, such as persistent writebacks, which is this PWB, and this pfence instruction. And just to sort of show you some example programs, these are 4 different examples. They're not sort of interleaved, multi-threaded examples. They're 4 different examples. They're all single-threaded. Just to sort of show you what goes on with persistent memory, I'll sort of talk through the 4 examples. And the way to sort of explain this easily, I think, is through this thing called a durable invariant. And the durable invariant is basically an invariant over the non-volatile memory. Okay? So what happens in this program here is, well, we're assuming all locations are initialized to 0. In this little program here, the writes can be persisted at any point in the execution. And so the only durable invariant you're sort of guaranteed is that either x is 0 or x or 1, and the same for y as well. Because one of the things that could happen is that the whole program could execute, and then both the x and y's have both persisted. Right. Now, if you insert these PWBs and pfences, you get sort of more guarantees. So the durable invariant you get for this little program here is that if y is 1, meaning if y has been persisted, then we're definitely sure that x has also been persisted as well. Okay, that's the idea. Now, notice that the PWB has a very special function. It kind of works together with the pfence. So if you just have the PWB by itself, then you don't actually get any guarantees. So the point of the PWB is to sort of to tag locations that you want persisted when you see a fence. Okay, so if you just have the PWB in this program here, then you actually don't get many guarantees. You're kind of back to where you were before. Okay, but one thing you can do with PWBs is you can sort of efficiently tag many locations, and then do a fence at the end, and then do a write. And here you can see that in this little program here, I've got 2 locations that I've tagged as PWB with PWB. And then I've done a pfence, and then I've done a write to y. Now, what I'm sure about is that if I have y equals 1 at the end in my persistent copy, then I'm sure that also x and y have also been persisted as well. Okay, so that's the nice guarantee you get. Okay, and sort of the second part of the story is that we kind of want to talk about sort of concurrent objects. And by concurrent objects, we want to sort of talk about linearizable concurrent objects. And in case you haven't heard about what linearizability is, it's a condition that was developed over 30 years ago, 35, getting close to now, by Hurley Wing. And basically, it sort of says that, provides a sort of concurrency guarantee that concurrent object sort of somehow takes effect instantaneously between its invocation and response. And you can sort of linearize these operations in a way that it's sort of consistent with the sequential order. With the sequential specification. That's the idea. so that's a very short tour of linearizability. I won't say any more about that. But essentially, there's been other conditions that have been developed, like durable linearizability, and that kind of extends this idea of linearizability to durable objects. So what does it mean for a persistent object to be correct? Well, it has to satisfy this one condition that, well, there's several conditions that have been developed, and one that's quite popular is this idea of durable linearizability. And so essentially what it says is, it's a very simple idea. You basically have histories with invocations, responses, and also crashes of, and you record all of that information in your history. And what you require is that if you take out all the crashes, then you get back a linearizable history. Okay, so an example would be something that looks like this. You've got three kind of threads executing a put and a get operation on some shared location. And it's basically just a store. Like you can think of the R as being some kind of store. So we've got to put R, again, I'm assuming that R is initially 0. So put R 1, thread 2, well, there's a crash, and then thread 2 gets something, and it happens to get 0, and then you notice that here you get R equals 1, right? And that looks a bit strange, but this is actually still durably linearizable, because what you can do is you can take out that crash, and what linearizability allows you to do is it allows you to sort of extend incomplete operations. And when you do this, you kind of end up with history that is actually linearizable, because you've got sort of 3 concurrent operations now, and you can linearize the get before the put, and then the put before the get, the second get, right? And that's actually linearizable. It looks a bit strange, but it's actually something that's allowed by durable linearizability. Okay. So that's the story of the background. And so what we're interested in is developing concurrent objects that are correct on non-volatile memory. And we want to, well, what are the options? One option is to sort of develop everything from scratch. You know, you've got this new kind of hardware, and you develop the implementation from scratch and prove it to be correct. The other option is to sort of do something a bit more clever, which is to sort of take legacy code, legacy algorithms, and then sort of transform them to this new paradigm, if you like. Okay, and then what we're interested in is understanding whether this transformation is actually correct. Okay, that's basically the essence of the paper. And a lot of people have tried many different, proposed many different solutions for the second option, which is this transformation. And for durable linearizability, there are a number of proposals. There's another correctness condition called buffer durable linearizability, another proposal called montage. What we're interested in is this particular one, FLIT, which was from, I think, last year or the year before. It provides a very simple way to transform concurrent linearizable objects into durably linearizable objects. Okay, so what it basically does is it provides a library, and it provides 3 operations, a library write, a read, and a complete operation. And what you're expected to do is you're supposed to take your linearizable object, replace all the reads and writes by libwrite and libread calls, and then before the operation completes, you call this complete thing to sort of do some final cleanups. That's essentially what you do. Okay, and yeah, so the library is super simple, right? So what you do is whenever you see a write, you start by calling some pfens. There's something called a flit counter, which you increment using a fetch and increment, which is a read, modify, write. Then you perform the write itself. Then you perform a PWB. So this PWB is, oh, by the way, flit stands for flush if tagged, right? And so what we're doing is we're trying to tag things using this PWB. So here we're tagging the write that we've just written. Then we do a pfence, and then we do another decrement of this flit counter. Okay, I won't go through the details of this algorithm in detail. The interesting bit is in the read. What's happening in the read is that the read is sort of checking that there's no concurrent write that's being executed at the moment, and you can sort of work that out by looking at the flit counter. So if the flit counter's value is greater than 0, you know there's a concurrent write that's being executed. So what you then do is say, okay, well I better make sure that later on I'm going to flush this value. Okay, and the way you do it is you sort of tag that location as being something that I've read that potentially is being written concurrently by another thread. Okay, that's the idea. And finally, there's a complete operation. Like I said, it just does some cleanups, but the cleanups are super simple because you just do a p-fence at the end, and it makes sure that everything that you have read that is potentially unpersisted does become persisted. Okay, that's the idea of FLIT. Yeah, quite simple, I think. Okay, and the theorem that we want is, or the theorem that is also stated in the paper is this idea that you can sort of use FLIT to transform algorithms from a linearizable algorithm into a durably linearizable algorithm. And what we mean there is we're replacing sort of the reads and writes in the object O with calls to the FLIT library instead. Okay, and that's basically what we tried to prove. Well, what we did prove. Well, we started by trying to prove it, and then we actually proved it. And the other thing that sort of the other complication that comes up is the memory model itself is not as simple as just this writing to shared memory directly. You kind of use this TSO memory model, which is the memory model from Intel, which means that you have these store buffers that get in the way. I won't go into the details of these, but if you've seen any weak memory model talk, then you probably may be familiar with this kind of thing, right? There we kind of have to think about, well, what do the persistent writebacks mean, and what do the p-fences mean, and so forth, and there are some proposals there. Okay, so when we do this sort of transformation to the actual hardware, we end up with code that looks a bit like this. Now we need to give some semantics for all these instructions, and well, we can do that because Ori and his then postdoc Artem wrote this nice paper about how you can sort of actually give a semantics and operational semantics for this for these persistent x86 instructions, and that's the semantics we use. Okay, so ultimately we end up with sort of a more complicated version of the theorem that looks a bit like this. Where we're not only talking about FLIT, but we're talking about FLIT executing in px86. So it's actually, it's in a reflection of a real implementation. That's kind of what we end up with. Okay, well, how do we prove this? There's a number of steps. Like I said, the proof is literally breaking it up into smaller and smaller problems and proving each of these smaller problems one little bit at a time. Okay, and so what we did first is came up with some kind of intermediate spec. So this jump from SC, sequential consistency, over to FLIT with x86 is pretty complicated, even though FLIT itself is quite simple. That jump is more complicated than one might expect. So essentially what we did was we came up with this intermediate library called plib, which is a persistent library, and it basically sort of captures the essence, we would say, of FLIT on px86. So that's step one. Step two is sort of to prove that if you can replace the SC, this SC over here, which is sequential consistency memory model, by the plib library. Okay, so this is an abstract library, and we can sort of do that replacement. And this replacement itself sort of guarantees that you end up with a durably linearizable object. Okay, that's the idea. And now we have plib over here. Well, we can actually just, we know that refinement is monotonic, so we can actually replace the plib gradually by FLIT executing on x86. So that's the three main proof steps. And I'll sort of briefly talk through, I don't know if I've got much time. Few minutes, yeah. Okay, I'll briefly talk through some of the steps. Okay. So the plib spec, you're probably better off reading the paper, because I'm just going to give you a brief idea of what it does. Like I said, it abstractly captures the essence of what FLIT does. And the library sort of tracks, again, abstractly, every read sort of tracks the write that it read from. And then when you're doing writes, you have to sort of check certain things, for instance, that all previous writes have been persisted, and if you've got any sort of dependent writes, then those are also persisted, kind of thing. And then sort of, okay, well, there's a formal model, and you do some standard things like build models, essentially, right? And there's also this log, which is sort of used to sort of do this sort of tracking of reads, and each read and write has some flag that tells you whether or not something's persisted and so forth. Okay, all right, details. And you end up with some automata that looks a bit like this. Details are in the paper. But when you're doing reads and writes, the library sort of double checks that in the log that you're doing the right thing. Okay, it's doing the thing that I just said in the previous slide. For instance, when you do a write, you're checking that all the persistent dependent writes from previous that you depend on are already in persistent memory, kind of thing. And only then can you perform a write. And so forth, right? And then there's sort of many details there that I'm just going to gloss over, kind of thing. But yeah, again, feel free to please read the paper. Okay, so once we have that, we have done this. Okay, so next we need to prove correctness of this theorem, but this time we're proving this transformation part, but with SC replaced by the plib. And again, so we transform this into a refinement problem. We can use results from many years ago. Okay, I'm going to skip this completely. But you'll just have to believe me that ultimately we end up putting a tick there to say, yeah, that's been done. Okay. So that was step 2. And then the final bit is replacing this plib by flit executing on x86. Okay, it's the final refinement that you have to do. And again there, it's split up into 2 further smaller proofs where we kind of developed another intermediate memory model called weak PSC, which is, I guess if you're not in this literature, then maybe you won't find it so interesting. But it's sort of SC strengthened with persistency, but again weakened slightly to cope with certain things that Intel x86 allows. So that's the idea. And now this was, I would say, a standard proof. It didn't involve any sort of transformation or anything like that, but still difficult. But the thing with this is that this has been mechanized and it's available as part of our artifact. And the proof was done by Gerhard Schellhorn and Stefan Bodenmiller at Augsburg. But yeah, that's there. Okay, so that's the final tick, and that gives us our final theorem. And there's the summary. So essentially, hopefully I've told you that libraries such as flit, mirror, and so forth give you some way of transforming linearizable objects into durable linearizable objects. And it's actually possible to prove it, but it involves some amount of effort and a big team. Thank you.
We have time for a few questions. Yes, Sankal.
Thank you. Very cool work. Very nice to hear that you've mechanized the proofs. How do you mechanize them? Can you talk a little bit more about the details?
Yes. So
interested to know how you model all the behaviors and what do you mechanize them?
Yeah, I mean ultimately all the models are represented using I/O automata, input-output automata. We could have used any theorem prover, really, but the theorem prover that's developed and that Gerhard uses, Gerhard Schellhorn, who is the main driver of the mechanization, is KIV. It's called KIV, Karlsruhe Interactive Verifier. And yeah, if you want details, you can check out our artifact, and you can say, yeah.
Is there an assumption on how O of SC was proven, i.e. if prophecy variables were used or not?
Yes. So there is a notion of a prophecy variable that we had to use. Yeah, so it's well spotted, actually. So actually, let me just sort of double check that I understood your question correctly. Which bit were you talking about?
If you prove O of SC linearizable, are there restrictions on what techniques you can use to prove O of SC?
Well, no. O of SC is being linearizable is an assumption.
Okay. So there's no, you can transfer whatever technique was used to prove of
Yes. So O of SC being linearizable is an assumption. There is a prophecy variable that is used. I might use this sort of opportunity to sort of point this out. When we're considering these sort of traces, you have to be careful. Well, we want to do it in a forward manner, but you have to kind of know that the thing that you're reading from or writing from is going to be persisted at the end. Okay, so that you kind of do have to leverage information from the future and bring it to the past, kind of thing. Yeah, but you can read out our paper for that.
Thank you.
Okay, so let's thank the speaker again.
Okay, thank you.
excuse me, for AV, can you just reset the feed because it froze. USB-C?
I don't know, I never used it.
There's on the other side something like USB-C. Did you try before?
No, unfortunately, but
Did you try it before?
unfortunately, no. So
It's not just a lock. Okay, let's. Do you have your slide somewhere? And it's Linux or it's which OS is this? It's Windows.
yes.
Problems with connecting. Do you have slides somewhere else? Posted on the web? Could you put them somewhere?
Yes, I think so.
It's not
No, but
another laptop also doesn't work. So it's something in the AV setup. I don't think it's a laptop. But since you just had it, maybe you just wanted to see. You have had your live or?
Yeah, it was directly.
Okay, so let's try that once again.
Not connected or?
Three laptops, none of them manages to go through.
Yeah, sorry. I think it's the same story.
Something happened at the end of your talk.
Yes.
What is this?
It's your it's their feed.
Okay, maybe try again.
That's not mine.
Problem with persistent memory. Okay, that
looks better, but
okay. Try again.
want to touch it.
so I'll just see what it goes. Okay. So thanks for the introduction. So this is joint work with Markus Müller-Olm, Christoph Orem, and Jens Gutsfeld. So to start, we consider the following example scenario, which I will use as a running example throughout this talk. So suppose we have a server that consists of a main thread, and this main thread can receive different kind of requests from different clients, and it processes each of these requests by starting a worker thread that then processes these requests and then gives a certain response to that request. Okay, and in this scenario, we now want the system to satisfy the following properties, which I refer to as properties P1 to P3 here. So first, the main thread should repeatedly accept new requests. And then second, we want that worker threads are only spawned by the main thread and not, for example, by other worker threads. And they should only be spawned if the main thread has accepted a request and not at any other time points. And third, we want that worker threads are also only spawned if we are inside a certain procedure called PR. For example, because this procedure performs some bookkeeping about all threads that are currently active. Okay, and we now want to verify that our system indeed satisfies these three requirements. And so these properties are essentially temporal properties of executions of the system. So this looks like a good way to use verification by model checking in order to achieve this. And in order to do this, we have two things to do. Namely, first, we need a formal model in which we can represent this example scenario here. And in particular, this model needs to support some notion of dynamic thread creation, because here we have a main thread that should dynamically spawn worker threads during the execution. And it also needs to support some notion of procedures so that we can even reason about the third requirement, P3 here. Okay, and second, when we have a formal model, then we will also need a specification logic that we can use for indeed specifying our three properties here. So for the formal model, we use an established model called dynamic pushdown networks, or DPNs in short. And this model essentially takes pushdown systems and extends them with dynamic thread creation. So during execution, we can now have multiple threads. Each of these threads can behave as in a pushdown system. So during the execution, each thread is in its own local control location, and it can operate on its own stack. And all threads can progress like that independently of what the other threads do. But then additionally, each thread also always has the option to just spawn new threads at runtime. So this is a quite useful type of system for modeling concurrent programs, because we have stacks for modeling recursive calls, and we can model multi-threading. We can just dynamically spawn new threads. Now we model executions of this model as graphs, and here you see an example. So each node in this graph corresponds to the local configuration of a single thread of the execution. So for instance, in the first row here, we have the nodes for the initial thread, and then the edges between these nodes just specify which type of action the thread performs when moving from one configuration to the next one. So we have a call edge if the thread pushes some symbol to its stack. We have a return edge if it pops some symbol from its stack. And we have an internal edge if it performs just an internal step. And moreover, as in nested words, we also use nesting edges, which are depicted as these curved dashed edges here to connect call actions with their matching return edges if they exist. And finally, when the thread spawns a new thread, then we also just add a spawn edge here, which connects the position where the thread is spawned to the first node of the new thread that is spawned here. And you also see that all nodes are labeled here with some set of values. So these values are just atomic propositions here that we will use for specifying basic properties in our logic. So we just say that each node is labeled by all propositions that holds in the corresponding local configuration that is represented by this node. So maybe you are wondering why we are using graphs for modeling executions of our system, because typically the semantics of DPNs or similar models is defined as an interleaving semantics. And then we would define something like a global configuration that consists of multiple local configurations that each represent the state of one of the current threads. And then a step in this semantics consists of a step of one of these underlying threads, so that we can then reflect different interleavings of the threads in different executions, because executions are then just sequences of such steps, and thus, well, two different interleavings just mean that we have two different sequences of such steps. But one big problem with this kind of semantics is that it often allows the encoding of the intersection problem for context-free languages quite easily. And if this is possible, then this would make all our verification problems immediately become undecidable. And so in contrast, in our execution graphs, we do not have this notion of different interleavings. So if you go back to our example, here for these two threads, for example, this graph does not specify how the actions of the two threads are interleaved after the second thread is spawned here. So there would be multiple executions in interleaving semantics that all correspond to this single execution graph. And so this also means that we will not be able to reason directly about a specific interleaving in our specification logic, because this information is just not visible in our semantics here. But our execution graphs still contain some other useful information that we will be able to talk about. So first of all, it contains information about the temporal behavior of single threads of the execution. And this includes, in particular, information about the call and return behavior, which is given by the nesting edges here. And it also contains some information about the thread spawning behavior, which is given by the connection of the different threads via the spawn edges here. Okay, so what we want to consider now is model checking for DPNs. And the only approach for this so far is called single index LTL. And in this approach, we can essentially check single threads of the executions against LTL formulae. And well, this is sufficient for expressing some interesting properties, like our example property P1 here. But for expressing our properties P2 and P3 here, we need a more expressive logic, because P2 talks about when threads are spawned. So here we need to reason about some kind of the thread spawning behavior. And P3 talks about being inside some procedure. So in order to express this, we also need to reason about the call and return behavior. And our contribution thus is to develop a suitable logic here that we can use for specifying all these kinds of properties. And of course, we not only define such a logic, but then also investigate the corresponding model checking problem. So our novel logic is called navigation temporal logic, or NTL in short, and its syntax is defined here. So an NTL formula is always evaluated in a given node of an execution graph. And then first we have atomic propositions to state that, well, some proposition holds in the given node of the graph. Then we have the standard Boolean operators just as usual. And then most importantly, we have these formulae of this form next f phi. So these formulae can be used for navigating through the graph by saying that from the given node, there exists a certain successor node in the graph, and then this successor node satisfies the formula phi. And the parameter f here is, specifies which type of successor is used here. So we have 6 different successor types in total that we can use for following the different kind of edges that we have in our graphs in different manners, either in a forward or in a backward way. And 4 of these successors come from a logic for pushdown systems named carré. And so these successors can be used to navigate to different positions inside of a single thread. And we then also add 2 new successors here so that we can also follow the spawn edges in the graph, either in a forward or in a backward way. Okay, and then we also have a least fixed point operator. And with this operator, you can express all the classical modalities that you may know from LTL or carré, like until, finally, globally, and so on. And so this is an example of a formula that expresses that the formula phi holds finally on the path that follows F successors. So as you see here, these modalities also come with this parameter F here that specifies which path is considered here by saying which type of successor we want to move on from the given node. But we can now also combine multiple of our successor types inside a single fixed point formula for expressing even more properties that we, for example, could not express if we just had an until operator for each single successor types, as we do have, for example, in LTL or Carré. And this is an example of such a formula. It specifies a very reasonable requirement here, namely that the property phi should hold just in an arbitrary node in the graph. And here we need two different successor types to express this, because in order to reach all nodes of the graph from the initial node, we need to move forward both inside of the current thread, but we also need to move to new threads when they are spawned. So that's why we have two different successor types here. Okay, so now let's go back to our example properties and look how we can express them in this new logic. So first of all, you see that all our formula here start with this special globally modality at the beginning. So this is just a dual operator to the last example from the previous slide, which just means here that for every node in the graph, something holds. And then the first property, P1, can be expressed by a simple LTL formula inside this globally modality that just says, well, if we are in the main thread, then we always eventually accept a new request. And so this is an LTL formula here, but thus it's also an NTL formula. And for the second property, we can express similarly that if we are in the worker thread, then some other condition holds. And so what we want to say now is that at the position where this worker thread was spawned, something holds, namely that at this position, we are in the main thread and we have accepted a request. And well, fortunately, we have a next operator to express exactly that. So the successor type that is used here is one of our new successor types that just moves from a given node to the position where the current thread was spawned. Okay, and finally, our third property can be expressed by this formula at the bottom. So the successor type, so this next formula that is used here just follows a spawn edge if it exists at the current node. So that this here just means if we spawn a worker thread at the current node, then this formula at the right holds. And then the successor type that is used in the finally operator is called the caller modality, and it just moves backwards to the latest previous call position that has not been matched so far in the thread. And well, using this in the finally operator like this here, then just means that at some previous call position that is unmatched so far, procedure PR is called. And well, this then just means that we are inside this procedure because the procedure has been called before and the corresponding call has not been matched so far. Okay, so now that we've seen some examples, let's take a brief look at the corresponding model checking problem. So in this case, this means we have given a dynamic pushdown network M and some NTL formula phi, and we want to verify whether all executions of M satisfy this formula phi. And we use an automaton-based approach to solve this problem. So at the end, we will reduce the whole problem to the emptiness check of a certain automaton. And one type of automaton that we use for this are called two-way alternating parity tree automata. And so we want to use these automata because their features very nicely match with the definition of our NTL formula, which makes the encoding of these formula into these kind of automaton very easy. And so one minor problem here is that these automata work on trees, as the name suggests, while our executions are actually defined as graphs and not as trees. But this is in fact not a huge problem because we can just do a simple transformation to transform these graphs into trees. And so what we essentially do is we just discard all the return edges in this graph. So this is indeed a tree now. And this is a useful transformation because first, we did not lose any information here So we could retrieve all the missing return edges just by inspecting all our remaining edges here. And the set of all trees that are obtained from execution graphs by this kind of transformation is a regular set. So this also means that we can use a tree automaton to recognize all our valid input trees that we even need to consider. And this transformation now allows us to use these two-way automaton to check whether an NTL formula is satisfied at a given node. And this feature, so two-way means here that we can navigate freely in the tree, both upwards or downwards whenever we want. And this makes it easy to check our different next formulae, because in order to check that the formula next f phi is satisfied at some given node, where we can just move to the desired successor node wherever it is in the tree, and then check whether formula phi is satisfied at that node. And we can then indeed reduce this whole model checking problem to the emptiness test of an automaton. And finally, we obtain that the whole model checking problem for our novel logic is x time complete. And more precisely, it is exponential only in the size of the formula, but in particular, it's polynomial in the size of the model. And well, usually in model checking, it's the model that might become very big and not the formula. So this is actually quite good here. And this is in fact the same complexity that we already have for LTL model checking against pushdown systems. But well, now we considered dynamic pushdown networks here, which are strictly more powerful than pushdown systems because they also support dynamic thread creation. And we developed our new logic, NTL here, which is strictly more expressive than LTL for single threads because it also allows reasoning about the thread spawning and the call and return behavior. It's both not possible in LTL for single threads. And besides model checking, we also considered the satisfiability problem for our new logic, and we show that this is also x time complete. Okay, and finally, for future work, we also want to consider some more powerful variants of DPNs that also allow synchronization of different threads via locks or communication between different threads via communication channels. Okay, so that's all. Thank you for your attention.
We have time for some questions.
So the threads, they are completely independent in the execution. It's like disjoint parallelism, right? And
yes.
this allows you to, because now every linearization of the tree, every total order of the spatial order is a possible execution. But this is no longer the case when you add locks or when you add communication. So then the trees will no, I mean these graphs will no longer be useful, right? I mean, can you still use the graphs when you add locks or when you add communication? Because then not all interleavings are possible.
So that's true. So we need to consider the fact that so I think we can still use the graphs, but you're right, we have to keep in mind that we have to check that whether this is even executable at all and how executions are possible then. So some more work to do then.
Did you look at the possible connection with what people call spatial logics? So logics, modal logics that talks about distribution and trees and processes moving. For example, the ambient logic of Cardelli and Gordon, and there are many other instances.
Sorry, I'm not understanding.
So spatial logic, it's a category of modal logic that talk about space. And so you can also add temporal modalities. Did you look into that? Or?
So I'm sorry, I cannot say anything about this yet.
Okay.
It's too old.
So maybe just one question that's related to Andreas. So and then we move to the final talk. So do you think if you only retrieve the Boolean result of a thread, that you will still be able to use trees to represent things without loss of information?
So no locking or
so I just want to know, okay, did this spawn thread result in a true or in false when it was finite?
Yes, so this should be possible, yes.
Okay, thank you. Any other questions? Okay, so
your examples, they did not talk about the call return discipline, but I guess that you can still express things like some function is not called before some other function has returned,
yes.
like in caret.
Yeah, yes. Everything that you can express in caret, you can express in this logic.
Okay, good. So then if there are no further questions, let's thank the speaker again. And so we can set up the next talk. Yes. So the final technical talk of this session is going to be borrowable fractional ownership types for verification. And the talk will be given by Takashi.
So let me start my presentation. I'm Takashi Nakayama from the University of Tokyo. Today I'm going to talk about our research named Borrowable Fractional Ownership Types for Verification. This is a research summary, and our research is about automatically verifying that the program with mutable references does not involve the assertion failure in runtime. And we solve this problem by translating the original program to the more pure functional programs. Our research is about its combination of two existing methods leveraging the ownership types. One is consort, and another is rusthorn. And both these two use the ownership types in so different manner that they serve as a complementary to each other. So let's move on to the background of our research. Again, the target of our research is the program with mutable references. And this kind of program is known to be difficult to verify due to aliasing references. For example, this is a simple program with mutable references that the naive verification method fails to handle. And the comments on the right side is a naive refinement type trying to verify this program. At the first line, the variable x is initialized as a reference that contains the integer value 0. And the type of x is initialized as like this. And that's the second line. And at the second line, the y is initialized as the aliasing references to x, and the type of y is the copy of the type of x. The problem arises at the third line because here y is updated to have the integer value 1, and at the same time, the aliasing reference x is also updated to have value 1. Now, however, we successfully changed the y's type, the naive refinement type fails to update the type of x, and therefore that results in the verification failure. So as we see the types, it says that the sum of x and y is 1. However, indeed, it is 2 because it's 1 plus 1. From now, I will explain the two existing approaches to tackle this problem. using ownership types. The first one is consort. A consort applies fractional ownership to refinement types, where real number or quotient number R are given to each references as their ownership. And here, the R equals 0 means no ownership, and R equals 1 means the full ownership. This example program is while bit modified, almost the same as the former one, and that confirms the sum of x and y equals 2. However, the comments on this page is the typing from the consort type system. The difference from the naive one is here we can see the refinement reference type have ownership 1 in its type, and on the upper part of the type. So then at the second line, the reference y deprives x of all of its ownership and refinement, and therefore the refinement of x becomes to have no information about its content as like true. And since x has no information about its content, we don't have to update the refinement of x while the y is updated and updated. And however, we should retrieve the information of the content of x, because to verify that line, because it uses the content of x. So to do this, consort utilizes the alias information gained by the separate alias analysis, so that we can redistribute ownership to x and y. In this example, the alias analyzer can detect that x and y as alias easily. So consort can insert the annotation of alias x equals y here, and and then thanks to this, consort type system can redistribute the refinements and ownership to x and y, and we can see that the assertion of the last line successfully verifies. And here, the ownership of 0.5 means the references are read-only. That is, the x and y can be read but cannot be updated. Sorry. So let's move on to the other approach named Rust horn. Rust horn is a verification method for the Rust programming languages, and which has a unique ownership type. We call it borrowable ownership with lifetime. So this is an example of the Rust typing. It is not refinement types, but in the Rust type system, the reference type is endowed with the lifetime, which indicated by the alpha or beta here. And this represents the abstract point at which those references are not used anymore. In this example, x has a lifetime alpha and y has a lifetime beta. In addition, Rust type system has a unique feature named borrowing, which allows the temporary lending of the ownership during a certain lifetime. In this example, the reference y is borrowed. The reference y borrows the ownership of x during its lifetime beta, as seen in the diagram. And during this borrowing, Rust type system disables the type of x here. So, and Another key point is we have an annotation of in lifetime beta here, and this means that white lifetime beta it ends here, and this is inserted by the lifetime analysis by the Rust compiler. And this enables Rust type system to dispose of the reference y here and re-enable the type of x here, and we can use it again here. So once typed, Rust can distinguish whether each references are borrowed references or not. And using this borrowing information, Rust conducts verification by eliminating all references by converting them to the pairs. So this is the example conversion for this program. This is a bit complicated, but the key point is that the borrowing reference y is converted to a pair of yc and yo here. And here yc is the normal integer that represents the current value of y, and yo is the non-deterministic integer that represents the future value of y at the end of the lifetime of beta. And thanks to this translation, we can see that here yc has the integer value 1, and looking at the assert statement, and this assumed statement means that the formerly no non-deterministic integer yo has actually a value, integer value 1. So by looking at the third line, we can see that the x equals 1. And finally, we can easily confirm that the assert statement at the last line would never fail. So let's move on to our proposal. So we have seen two existing approaches. Consort uses fractional ownership, which is good at quantitative ownership sharing, and Rusthorn utilizes the aliasing information in its typing. On the other hand, Rusthorn uses borrowable ownership, which is good at temporal ownership sharing, and Rusthorn utilizes lifetime information in its typing. So the idea of our research is combining these two to get a more flexible method. Now we propose borrowable fractional ownership types. This is a type system that combines consort and Rusthorn. So this is the syntax of our type. And here we consider only the integer and the reference of integer. In other words, we don't consider the nested references like references of integer here. Anyway, here we can see that the reference type has both lifetime and the fractional ownership on the upper part of its type. And in addition, the reference type also has borrowing information B on its lower part, and this consists of lifetime and fraction, which indicates during which lifetime and how much ownership the reference lends to the others. So, for example, please look at this program. In this program, the reference x and y is initialized as the aliasing references, and then we use both of them and to initialize the variable a, and then we update y, and finally we update x and try to verify the assertion. So our type system can type this like this. So here y borrows the ownership of X depending on the program point. So, but yeah, this is, maybe it is a bit hard to read this on the slide, so we show this typing as a diagram like this. So after the first line, X lends 0.5 ownership to Y, and it increases to 1.0 ownership, full ownership after the second line. And after the lifetime of Y, the lifetime beta ends, the X retrieves all of its ownership. Sorry. So we designed our type system based on consort, and this type judgment is of the form like this. And we have here 3 typing context and 2 updated environments, since our type system is flow sensitive. And this is a representative typing rule that for the let statement. And the key point is we express the ownership sharing as the type addition. The definition of type addition mainly consists of two rules, one of which is express the quantitative sharing of ownership, and another is shows the temporal sharing of ownership. Yeah, by our type system, we can uniformly type the example in consort and example in Rusthorn. In other words, our type system successfully subsumes the both of them. And our type system has more expressive power than both. As for example, this program cannot be typed by consort nor Rusthorn, but our type system can handle this like this, but this is a bit large to explain here, so please read the paper if you're interested. So next, we explain the verification method using our type system. Our verification method is an extension of Rusthorn's technique. A main difference is that in our method, all references are converted to pairs. And another difference is the definition of borrowing. And in our type system, borrowing is the situation that a reference takes all the ownership of another. So let's look at the example before. And this example, X is deprived of all its ownership in this alias statement. So we regard this point as the point at which the borrowing occurs. And using this information, we can translate the original program into the program without references as almost the same way as the Rusthorn. So let's move on to our results. First, we have proved the well-typedness of our type system, and we also proved the soundness of our translation. That is, we show that a well-typed program will not fail if the translated program does not fail. And we also conducted preliminary experiments for some benchmark programs by manual typing and translation. We translate the original program into OCaml and verify them with the verification tool, Mochi. This experiment showed that our method successfully works correctly for the benchmark programs. So this is the related work of our research, but we skip this here. And this is the conclusion. The goal of our research is to automatically check the absence of assertion failure for the program with mutable references. And we propose the borrowable fractional ownership types and the verification method for it based on Rusthorn. and this work makes the ownership types more widely applicable in the context of automated verification. So thank you for listening. That is my
Any questions?
Yeah, are there any restrictions for the choices for the running times alpha and beta?
If it is correctly given, there is no restriction. However, yeah, the lifetime has the ordering, and the the given lifetime should have some total order in its typing. Is that mean?
Yeah, okay, so in general there's no restriction.
Yeah.
Thank you.
Thank you.
Any other questions?
Thank you. Thank you for the talk. I'm trying to understand the fractional ownership a little bit more. So does it have much other purpose other than counting the number of references, for example, 1 by n? Could you, for example, sometimes have ownership that's 0.7 and 0.3, or does it always have to be 1 by n?
So you mean the advantage from the reference counting?
Yeah, I mean, because in all the examples you showed, always had value either of half or 1 by 3. Can you, for example, have 0.7 and 0.3, or is it always basically just reference counting?
Yeah. Yes. There can be some example programs that uses multiple references, more than 2, and by using fractional ownership, we can divide the 0.5 ownership to 1/4 ownership and 1/4 ownership, and
so it will still always be of the form 1 by n.
Yes.
Okay.
Any other questions?
Just a question about that. Can you ever join them? Like, you know, often like with static reference counting, you can get 2 references which are a third each. We combine it to get 2/3.
Sorry, could you say it again more slowly, please?
So say you had a function which took in 3 references with a third ownership each. Could you define it such that it returned 2 references, one with a third ownership, one with 2/3 ownership?
Yes, you can define it.
In that case, you could get 0.7 and 0.3. Yeah. I was wondering, pardon? Oh, right, yeah. This seems to capture a lot of what unsafe Rust is useful with the, apart from trying to assert the type of things, a lot of unsafe Rust is just to get around proving that mutability is correct. How much do you think of the standard library could be formally verifiable using this?
I think this is applicable for also for the unsafe Rust, but yeah. Sorry. It depends on the program you want to verify. Yeah. Sorry.
I'm just wondering if you have any intuition of how much of the total unsafe ownership, unsafe usage, is this? Is it quite common, or is it?
Sorry. Sorry, I cannot understand your question correctly. So please, so let's talk after this.
Thank you.
Okay, good. Let's thank our speaker again. And now we'll have the closing of this conference and the announcement of the Best Paper Award.
Okay, thank you. Thank you for staying. I'll try to be quick. So a few statistics and then best paper. So we had 88 before desk reject submissions, and then 74. There were some papers that were desk rejected. 30 papers presented here. So it's 41% or 34%. I'm not sure how to count the desk rejects, how it is counted. Every paper got about more than three sometimes reviews, so 3 to 6 reviews. Among the 30 papers, 6 was there was a heated discussion, I guess. Among the 30 papers, 25 papers, regular papers, 1 case study presented today, and 4 tool papers. And there was also a lot of discussion, so the program committee did a lot of work here with, in total, if I counted correctly, 239 comments in EasyChair. So let me first thank the program committee. Some of them are here, not many. Let's give them a round of applause for the work. Next is statistics by country. I'm not sure what we can get from here. There is Estonia is perfect, 100% acceptance. So of course we have divergence. We want to have more divergence in this aspect and in others. Not sure what to say here. Okay, before I forget, I also want to thank the student volunteers, especially those helping us with all the technical issues that we had just now. So thank them too. We also had artifact evaluation. Sebastian Wolf was the artifact evaluation chair. He couldn't come, and he had his own committee. So VMCAI is a very dense timeline because we are somehow between other deadlines. So artifacts are submitted almost together with the papers. So of course, only accepted papers can have artifacts. And so 28 artifacts submitted and 14 accepted. These are of the accepted papers among these 28. So thank you for submitting papers, for submitting artifacts. I think we had a very nice activity in this edition of VMCAI. And I think, yeah, now we are ready for the Best Paper Award. So there was a nice contribution by Springer, so there will be also a monetary prize of $1,000. And the Best Paper Award, let's see if this animation works, goes to Correctness Witness Validation by Abstract Interpretation. That a paper by Simon San, Michael Schwartz, Julian Eard, Helmut Seidel, Sarah Lischer, and Veshal Vodjani. Sorry for mispronouncing some of the names. So you're welcome to come here, if some of you are here, I hope. Raina, come help me. We have paper. We have certificates and later also more. So the reviewers appreciated the originality of the approach and elegance of this approach. Later. By that I end my short part, and Andreas?
Yes, we have to thank the PC chats for the fabulous work. So after VMCAI is before VMCAI already tried to work on your paper for the next submission. See you next year. Bye-bye.